Now we are ready to begin the first session of this conference, and I would like to request Professor Tanushree Shahadas Gupta to kindly chair this first session.
Welcome back, and it's my really privilege to chair this first session, where the talk will be given by Professor Rupamanjari Ghosh. So she has, I think, kind of two feathers in her hat, because she is a very renowned quantum scientist, and unfortunately in India, starting from S.N. Bose, who later converted himself, we are very much theory oriented. We're very good at doing theory, and we are little bit, like to stay away from experiment. Traditionally, it's like. But S.N. Bose, who started his career as a theoretician, in fact, his master's degree was in mixed mathematics. It's not even physics. And I don't know how many of you know, he didn't have a PhD degree. I did. So, but this person and his work actually was combinatorial work. This is to do with statistics. Einstein made it more physics-like. But then he himself got converted to an experimentalist. He started with X-ray crystallography. So we have very few, at least in the old time, experimentalists in the domain of quantum. And I think Rupamanjari is one of the rare species from that time, when it was not very common to have experimentalists in India working in the domain of quantum. That's one of her feather. Her other feather is institute builder. So I think when you start an institute as an initial person, you do have to address many problems. And one of these is probably also the gender. So she can address the problem from both aspects. One as a practitioner, as a user, and another as a person from the administrative institution as well. So with that, I invite Rupamanjari to deliver her talk. You have 45 minutes, and please keep 5 minutes for interaction.
Sure. Thank you.
Thank you, Tanushree. Thank you for also having us all here on this great occasion. The inaugural session has stated a lot of the points that I had in my mind. So after I sent this title to the organizers, the issue of gender imbalance in physics, education, careers, and leadership, Tanushree asked me to talk about a bit of my science. So I tried to squeeze the two. So some of you know the old work, so don't get bored. But I'll try to sort of jump from one to the other seamlessly. And to start that, I discovered this photo. My father had kept it, and I don't know whether you can see it very clearly. On the left is, of course, Satyan Bose. There's an unknown person, my father's friend must be. The little girl on his lap is actually me. I did not know that I'll end up doing physics. And this was in 1962. You can make out my age by calculating. So this was quite something. I found it, and my parents are no more. My connection with Calcutta is kind of getting lost. But still, I thought I'll start with this as a homage. I wish I knew him better, but I was too young to cash on to these connections. Our houses are not that far. So I start at the beginning because time is limited. Let me give you a flavor of what I've been thinking. So as Rohini mentioned, it's actually not goal 4, goal 5. That even in UN Sustainable Development, goal 5 says achieve gender equality and empower all women and girls. For me, the important point is about decision making. How do you empower? Are you taking a part in decision making, or is somebody else's decision being forced onto you? That really is the key. So that's what it is all about. So it's already had gotten in there. And some statistics you already heard. I can go on and on about it. So I don't want to really, spend too much time on it. But the gender imbalance is staring at our face. Some positive stories from India, but even if you do a scrutiny of the data, you find several imbalances. But roughly, instead of 50%, you see these numbers in marked in red. So 30%, in 20%, 13%. So this is really something that we need to take into account and ask the question, why is it like this? So in India, if you look at it, I looked up, this is an old slide of mine, 2021. So again, instead of 50%, you find research scholars are about 31%, postdoctoral fellows, this is in India, about 29%, faculty is only 14%, and the numbers are down when one considers awards and accolades and leadership positions. As Tanushree kindly mentioned, there's a new private research university, Shivnada University, that was started, and I was the vice chancellor for 2 terms. And it sort of always, when I did my master's in Calcutta, I don't think anybody bothered the fact that I was a woman. The moment I landed in the US to do my PhD, it was a big deal. It was noticed as a woman. Prashant is sitting there. He was my junior in Rochester. So people start noticing as if you are a sample from the zoo. So everybody looks at you. You get noticed more easily because there are very few of them. For my supervisor, I was the first and the last woman student. I mean, so those are things that are a little funny, and cultures do matter. So the question that one should be asking, why is it still like this? And people would give you a lot of whys. Career in science, engineering, technology is a strongly growing sector of the economy and a major research area. Therefore, it's a demanding and tough option. But I would say that for both men and women. It's okay if I hold it. I mean, as teachers, we speak pretty loudly. So if you don't hear me from the back, you let me know. And online people. So one of the whys that I hear a lot, because recently with Rohini, we did a lot of work on competitive tests. And one statement that came out is, and I put it within quotes because I don't believe in this. Women tend to avoid competitive situations, whereas men prefer competitive tasks. Do you believe in this? So this is one reason that's given. The second one, of course, is the imposter syndrome, which involves feelings of self-doubt and fear that your own skills are not sufficient. You always, you feel like an imposter. A lot of people have it, even men have it, but perhaps more women are affected. This conditioning of women to think this way, I would, state that it's acquired through our socialization, and it's nothing inherent in us. It's socialization, conditioning that makes you probably feel that. And there are, of course, additional barriers, and people would say unintentional, like in a crowded bus, you step on somebody's foot, you don't want to, but it happens and you don't understand it. So there are unintentional barriers that put up along the career path of women in science. Some women ignore them, and you have enough examples in this room, but often at a very high personal cost. And I'm going to tell you what my philosophy has been in a minute, but before that, if you're interested, there's a very pretty old EEPS editorial, Getting Girls into Physics, Are We Saying the Wrong Things? And it's quite nice, it's written in a very professional way. But one point that I thought I would highlight for you to probably read it up later, it says we continue to treat girls as if they're proto boys. That's the major part of the problem. And I think we need to be more conscious of what the standard we are setting up for others. I did my PhD abroad, and I did not have a godfather or a godmother in India. That network is sorely needed if you take your first steps in the professional domain. I missed it. There are, of course, a lot of institutional sexism you face. I mean, let's just admit that that happens. Women have to work harder than their male colleagues to convince their colleagues and superiors of their abilities. You are not noticed. When I finally got a chance to chair selection committee meetings, this was pretty obvious. It was sometimes funny. The same CV, this is sort of seen everywhere. Similar kind of CV of a boy and a girl. For the boy, my colleagues in the committee would say, oh, he's a genius. Really great word. And for the girl, they would say, well, she's really hardworking.
Yeah.
Right? It's very common.
That's most common.
Yeah, it's very, very common, very hardworking. So I would ask, why do you say that man was a genius and this woman is just hardworking? And they would say, well, because her supervisor is a very famous man and did this and that. And the vice one is also a very famous man, but he was independent and all. I'm just saying these are anecdotes. I can go on and on, but my time is limited and the chair will soon get up. So let me just say that these are known stuff. These are known things that there are very few of women, and so sometimes they notice more easily. So it goes in your favor. Uh, my PhD work, which I'm going to talk about, is though it's very, very old. It was a post-deadline paper in a very good conference in Baltimore when I was still a PhD student, and I was the only one who was videotaped. And I always wondered whether the work was that good that that group from Maryland videotaped my entire talk. Nobody else was videotaped, or because I was a sample from the zoo, so I had to be actually videotaped for that. So you get noticed if I'm not present in JNU. I mean, I spent 24 long years at JNU in the physics faculty. 9 o'clock, if I'm not there, everybody would notice. I was the only female faculty out of 18 for a very long time till new faculty members joined. So it was it's kind of this. You have to work within that, and I don't want to go through this, but you know certain things are obvious. Security aspects. A colleague of mine who was quite fond of me is no more, and he has a daughter who wanted to be apparently like me, and he came and told me that, I don't want her to do physics. You work late night in your lab, and it's not very safe. We feel very so genuine concern of a father, and so these things we have to sort of work for. There are no proper crushes, etc., etc., etc. So my own experience in dealing with all of it gave me the advantage of understanding and prioritizing, which led to what I would like to call a creative leadership. It's creativity in your leadership role, which Tanushree has been showing somewhat here. I actually admired that, some of the traits, but you see that because you sort of know how to deal with situations which you have not seen before, and your team actually has no clear understanding of the purpose. So that feeling of purpose is something that leads to creative leaders. And that's something that I've seen. This is a picture that I borrowed from the net. I forgot to write the source there. But what is the point that was actually made by Umesh and others? Why should the society bother? It's not just about treating everyone equally. Two individuals are never equal. We are not identical, right? So what we are talking about is understanding the differences rationally and ensuring equity, not equality, equity, and making the best of everyone's abilities and choices. If you could do that, that's what you're looking forward. And I coined this term, I don't know whether it existed before, that we need a gender-rich society, not gender-neutral, not even the fairness to gender doesn't mean everybody should be treated equally. It doesn't work because we are all different. So what we are talking about is equity, which illustrated in this picture. But final justice probably will be when there are no barriers. We're dreaming about it. We'll see how to go about. So essentially, gender-rich society is both desirable from a morally correct positioning, but I will also show you that it's beneficial, which others have also talked about. And for physicists, it's really a commitment to excellence. Excellence by fairness. Because if you are free from discrimination, harassment, intimidation, or exploitation, excellence comes. Excellence is suppressed when you have all these evils running in your society. So that's when you commit to gender equity, then you're committing to excellence by fairness. Why should the society bother? Why is it economically beneficial? It has been stated already, but let me just say it very clearly. Again, when you are sitting in the selection committee, your idea is to engage the very best people, not just the best men and the next best men and the next best men, because you need to stay competitive in business. And we cannot be competitive in a global economy if half of our human capital is not allowed the opportunity to work up to its potential. There was a Harvard Business Review paper in November 2016. Title of it was something like Diversity Makes Us Smarter. Case studies were on businesses, but it applies to academic institutions as well. Diversity and inclusivity are not just morally correct principles for an institution, but it makes perfect business sense to promote them. And that's something I want everybody to remember. That's the way it should be treated. And so we need to prevent a division of men and women into two opposing interest groups, because then it becomes a net zero or often negative sum. It should not be that only women raise and fight for women's issues. I hate this term. These are not women's issues. These are common issues to be faced by everybody. So all right-thinking humans should be in this together. So that's our goal, and I'm so glad to see men sitting in your audience and in the inauguration. It's something that we have to do it together. These are not really women's issues, and it should come. So what I was saying that previously, that I'm product of a generation where some of us have made it in spite of the system, not because of the system. And I wanted to change this for my next generation. So this is the striving for excellence in whatever you do. This is when I took up the vice chancellor's role in Shivnada University. This is what was driving me really, that we need to change what we have faced. I quickly switch in the next few minutes that I have to talk a bit about the topic of this conference. And it's also very, very important. We are celebrating one century, but quantum mechanics itself is celebrating a century next year. So 2025 has now been declared International Year of Quantum Science and Technology as the 100th anniversary of the development of quantum mechanics. Development happened over a span of years, but 1925 was quite significant in the two formulations of quantum mechanics. So we are there, and I think it's also very exciting. You heard the secretary talk about it. Some of us have got dragged into this national quantum mission, and so the money is a little less probably for this right now. It's about 2,000 crore less for now, and then you'll see other departments adding up. But on quantum computing, quantum communication, quantum sensing and metrology, and quantum materials and devices, which probably spans all the other four thematic hubs are going to be set up. So there is a lot of scope for R&D and being driven by the government right now. And this is kind of late recognition, but the Nobel Prize in Physics in 2022 came in this area. Of this, Alain Aspect is a personal friend of mine, and these three gentlemen got it, and this is the citation in the Nobel Prize for experiments with entangled photons, establishing violation of the, I don't have the time to really talk about this, but maybe some other time, and finally, quantum information science. So this happened in October 2022, and I think it's not too old, so there's a lot of excitement in this. So I take you back, I will not even give you the full-fledged answer to it, just for the sake of people, including the media, who are not probably in the field. There is a lot of things that we knew, and old Feynman style, this is something that one could see that's a very familiar double-slit interference setup, in which instead of a regular source, you now have a very special source, which you either attenuate light to get not quantum source really, or actually create single photon quantum sources, which shoots one photon, one particle of light at a time to go through the device. Okay, I put a screen here with two tiny holes and a detector that can span the detection plane. If I close one of the holes, the detector detects light, say 1% of the time. If I close the other hole and open the first one that I closed, say it's a symmetric situation, you get 1% of the time, the detector is detecting something. When you open both the holes, they don't add up. It depends on the position of the detector, where the detector D is. Depending on that, sometimes you get no clicks, no detection of light at all. I have not explained the clicks, not really important for this time. So you understand that this phenomenon of interference is sort of prompted from optics. Optics has done many revolutions in physics. One that children are familiar with is relativity. The second one is quantum mechanics. So it had come from optics. So like to talk about this a lot. This is our field. So it basically you get puzzled that opening a second hole doesn't always increase the amount of light reaching the detector. What exactly is happening? So final lectures, the volume 3 first chapter he says that this about double slit experiment, that it's impossible to explain in any classical way, and it has in it the heart of quantum mechanics. It contains the only mystery. So if somebody says that I understand this, they're lying. That was the idea, that they're lying. Nobody really understands this. We know how it works, and because I know how it works so that we can apply it in situations for calculational purposes. So this is old story, you know that. So what happens if you shoot one photon at a time? The crowded slide, don't read it really. You get one tiny detection randomly on the screen. If you shoot it a million times, then this pattern emerges. So Dirac had said that we should think of the single photon as being associated with both paths simultaneously. These two paths interfere. So photons do not interfere with itself. There are consequences of reality and locality. Today, I'm not going to talk about this. So this is a very famous statement from a textbook by Dirac. Each photon interferes only with itself. Interference between two different photons never occurs. My experiment proved this wrong. It was possible to make two photons being emitted by independent sources interfere. And this is the entire field that has emerged. So I wanted to pick you back from there, way back in 1986 and 1987. So you can actually create sources with quantum states. And these are those old papers that I found, and I put it up here. The first one is the theory. And this is the same form, who are my juniors, and Mandel was my supervisor. And this is the experimental paper that we did. So this has now figured in textbooks. And this is a pretty readable book. This is a paperback version. There is a hardcover version from Jones and Bartlett as well. It's called The Quantum Challenge, and I did not know about it. A student of mine opened the page and saw it looked very, very familiar, and found out they are actually talking about my experiment in this short book, 3 pages is there. You can't really read it, so let me just say, I started with the Nobel Prize by aspirator in October 2028. My work is kind of sandwiched between Alain Aspect and Zeilinger. So they were working on calcium cascade in 1982. The square bracketed terms are mine. And that's the time that they say that through a process known by the intimidating name of spontaneous parametric non-conversion, a single UV photon can fission into two if it is passed through a nonlinear crystal. So this is something that we did at that time. And this is quantum non-locality, a new source. This is the first time actually it was shown, and a new experiment where this is very similar to the Bell inequality kind of things, but it is not really, I don't want to get into it. It's again a non-local effect, because when two photons are created by a fission of one, they're like twins. So even when they're separated far apart, so the quantum correlation exists because of the way they're created. So again, Dirac's explanation of interference works, but not the statement that he made. That turns out to be incorrect. This thing has figured even in popular science textbooks. Again, you can't quite read this, but the book is called The Age of Entanglement, and it's a story that was created out of it. And they came upon my experiment, but someone is not showing, but actually in the book originally it was written as my name working on his PhD. So assume that Arkush must be a boy. I mean, so she knew me though. I don't know how this mistake happened. And then after I made a noise about it, it got corrected. But so this is really something that was taken up by Zeilinger's group. This is the story that she cooked up on this, and this is how the entire thing happened. So for the students, the source of entangled photons that everybody uses, this is a very old diagram taken from my paper, around those days on this stupid printer. It is a nonlinear medium, so they are not linear. So the I2 in the bulk of a nonlinear crystal, which is not zero. Then only you can fission this. Efficiency of converting a pumped UV into two infrared is very, very low. But you have to satisfy this, what we call the phase matching condition, which is nothing but momentum and energy conservation laws. So within certain angles, these cones come out of the crystal, And this is the process of SPDC that everybody today is talking about in quantum computation. So we did it in the bulk, and that's the first ever experiment that was ever done. And this is how it took off. And this picture is taken from the linear Slater paper in Vienna, when these photon pairs emitted along the intersections of the cones are entangled in polarization. I'm not going into the details of this. So what this entanglement is what Einstein calls the action at a distance. So what happens to one of the particles in an entangled pair determines what happens to the other particle. It's all right when they're close by, but if one particle effectively, as it knows something about the twin instantaneously, so as if you're sending information at the at infinite speed to the other particle, it's nothing like that. It's simple point of quantum correlation, and this has become a resource for all of quantum computing. We have worked on this even later years as well, so I'm not getting into this. So a good question to ask is that, is there a door between the classical and the quantum world? You open it to go from, okay, I'm in my normal familiar classical world and I go to the quantum domain, and people used to think about it in terms of size. But that notion has also gone off. But in that book, also it talks about that quantum mechanics shows up in small enclaves within the classical macro world. The behavior of individual constituents that make up this world, for example, atoms and photons, they are described by quantum mechanics, but these particles are rarely isolated. And as they interact with the environment, they lose their peculiar quantum character. So this has been a challenge. So the central question also has been the mechanism of transition between the quantum and the classical world. The other side of the problem also, to make a measurement, not only one needs to keep the quantum system isolated, but also probe it so delicately that the measurement itself leaves the system's quantum nature intact. You've heard of the collapse of the wave function. So the moment you make a measurement, it changes to one of the states available to it. So it's a very fragile quantum effect, and observing that and making use of a system's quantum nature are tough and challenging task. It started all the way back. I don't want to get into it, all of you know, I'm sure. This is really illustrated by the Schrödinger's cat paradox, that if I treat the cat as well as a radioactive nuclei here as quantum objects, then when the radioactive nucleus decays, it releases this poison and the cat dies. And if it doesn't happen, then the cat is alive. Nobody in our regular world has seen a cat which is both dead and alive. So, but quantum mechanics makes use of this because these are macro objects. If you believe that they are quantum, then these kind of things happen. And this is how this parallelism is kind of exploited to create a quantum computer, as if to tap directly into the CPU of the universe. It seems like nature is working on those. We just need to know and make use of that. So essentially, this is something that everybody was working on. So a qubit is really a combination of these zeros and ones, not just zeros and ones, but a superposition of this kind is kind of an atom is upstairs and downstairs. It's a combination of no and yes. So it's like maybe, and maybes have a lot more information than just strict no's and yeses. And so how to produce, observe, and make use of these powerful information-rich states is the question. And major thing that people talk about is really the decoherence that I talked about. And there is a popular article that came out from Shankar Sharma saying quantum computing has a high problem. And what he talks about is that this essentially the thing that the main issue is that quantum states disappear in the presence of environmental noise. How do you isolate a quantum system to prevent decoherence for photons? It doesn't really matter much. They don't interact much with the environment. They have their bandwidth problem generated from source, but for everything else, we need to work about. I don't want to get into the details. They have written something. I'll show it on Monday when I will talk at the Chanchal Mujumdar workshop. So some of these I'll talk about it there. But essentially, this concept of decoherence appears in physics quite a bit in handling different kinds of problems. I talked about it, and the reason I'm pointing out is that we have worked on this quite a bit with my students in JNU, and so this is one aspect of the things that we did. More such work is needed, and there's some very specific questions you can ask related to differential quantum computing, and we need to understand it to control it. And I think that's essentially is the point. What I want to spend 5 more minutes on is the concept of a quantum memory. Our group has worked on various aspects of laser physics, nonlinear dynamics, but this is one strand that sort of connects to the theme today. And quantum memory is, I'll give you only one example because again, it's totally biased towards our research. And this involves a phenomenon called EIT, electromagnetically induced transparency. EIT in short, as the name suggests, is induced transparency, a material that was opaque. I somehow turn it into a transparent material on resonance. So cancellation of resonant absorption, this is something that was known to people in 1988, 89, and 2 groups, one in Russia, one in US, had actually worked on it. But it became popular later. And to make you understand this in a very simple way, this is something that we learned in Jackson and other textbooks. When you actually shine light, which is shown as this red omega, and the energy separation between the atomic levels is h bar omega naught. And don't take it literally, these are pictorial cartoons, representation of the actual thing. Then when you shine light, then absorption peaks when this delta detuning is 0, right? So the population gets lifted up, and the dispersion has this anomalous curve, a very negative dispersion that you actually see. What happens when I apply a second laser at the 3rd level? And in the presence of this control laser, where there was maximum absorption, the population was getting lifted up, so this laser was getting absorbed. Now I have a dip in absorption, that means a transmission. So boom, this light sort of goes through. So that's the transparency we're talking about. The opaque media suddenly becomes transparent when I apply this control laser, and something very funny happens to the dispersion curve as well, that this extreme positive dispersion that you see actually can be utilized to something that we call slow light. Now, slow light, you would think it's not such a big deal because light goes through vacuum at a very fast speed. But if you shine through even glass, water, air, its speed goes down, group velocity slows down. But that is of the order of 1.5, 1.3, or in semiconductors, maybe 6. Here we are talking about group dispersions of the order of 10 to the 6, 10 to the 7, 10 to the 8. So I can slow down light to sort of walk through the material at the speed of a cycle. Okay, so if you can do that, the natural question that you would ask, can I actually stop light inside this material? If I stop, that would be a model for a memory, a storage. So this is something that we talked about, this using 1st order dispersion theory, that your group velocity is given by the free space speed divided by this group index. So how slow can it get? And this leads to this concept, but before that, again, you see it's the fundamentally quantum idea that we talked about in the double slit experiment. One is that a probabilistic interpretation, that you can't really say which way the photon went. You can just say that the probability of going through this one is 50, probability of going through this one is 50. Here also the same thing happens. And again, you have to add probability amplitudes, horrible names. Probability amplitudes are indistinguishable paths. Okay, the 2 photons do not interfere. Here the 2 paths interfere. And that you see in the physics of the CIT, one way of looking at it, there are multiple routes of excitation from the ground level to the up level, which is for the probe. One is direct, D to A. The other one is mediated by the coupling laser. So these 2 paths interfere and cancel the probability amplitude for absorption from B to A. And this is really the principle of the induced transparency that you see in EIT. And like the double slit experiment, there is an inherent coherence time involved, and that is to do with the spin coherence of these 2 lower levels that you created by the control field. So this is something that we worked on. And what is interesting in this is that you're talking about bulk quantum mechanics at room temperature. That makes it feel deployable. And people are working on this. Again, I would not get into the details of this, but this work couldn't have been possible without my French collaborators. This is my house in JNU, and very Indian-looking French lady, Fabien and Fabienne. They have become good friends, and this work was done with helium atoms, and then we got excellent grades. So there's some nice things about Shashifra, but all of that came out. A lot of papers that came out. This is only our work that I'm citing. So this also has some physics, interesting physics in it, that if I could actually slow it down, you would ask the question, can I make it faster than C? The answer is yes. And all hell would break loose because you would say that it then violates Einstein causality. What's the problem of transferring information faster than the speed of light? The main problem is if you could really do that, you can go to your past, kill your grandfather, so you would not be born. This is called the grandfather paradox, right? So causality is a fundamental principle in physics, which we all believe in. There is no first principle proof of it. Causality is believed in because otherwise cause and effect relationship would get all messed up. So you cannot really go faster than speed of C. What cannot go faster than speed, than the free space speed, is the transmission of information. So the question that I ask is that if this is the formula that I'm getting, and this ng, the group index, like your refractive index, can actually be negative or can be less than 1. If it is less than 1, your group velocity is actually greater than c. This comes from first principles. It doesn't violate Einstein's causality. It basically tells you that this Vg doesn't carry any information. This has to be looked into carefully, but I just want to leave you with this thought. So it's possible to get into superluminal transmission, and this is very, very counterintuitive, but it does not violate causality. In experiments, we actually showed this Vg negative part seamlessly from Vg positive using EIT in helium form. We have had fun adding another level, creating a tripod, led to another thesis in JNU, etc., etc. So essentially, you can actually manipulate the atomic properties, optical properties of transmission and absorption by shining another laser. Nice thing about this field of optics is that unlike particle physics, nothing gets lost. When you turn off the control field, nature is restored. So that's something that's very, very nice, but this control can be seen. So you can create switches, you can create a memory. So basic physics part is that photons with zero rest mass are not possible to localize, right? Because they cannot be at rest. Here, we are not talking about photons with zero rest mass. We're talking about dressed photons. They're all dressed up because these photons are now interacting with matter. So the new, the dressed photons, those are in condensed matter called polaritons. We also have something very similar. They are non-zero rest mass, and that can have zero velocity in a moving frame of reference. So physics is safe, but it's a new way of doing physics. And there are other people by other methods, don't get confused. I just quoted this publication, I put it here. It's also stopping of light by a different method. So incoming light will carry the information that you code on the horse. And then when the light stops, that information is stored in the collective atomic excitations. Remember the Raman coherence I showed, it all depends on that Raman coherence time. And to access the information, the control laser is turned back on and out comes the information. So it's really possible to have a flying qubit get into a stationary qubit, and you can have storage and retrieval protocol. So retrieval at will, not random. When you want, then only the memory gives out the information. And there's a lot of reviews that you see. People have gone ahead with this concept, and final thing is not out, and you can actually see this. Room temperature environment Institute of Science, people have actually managed to do room temperature cesium cell, and the storage time was 1 second. It's quite a remarkable feat. In 1 second, you can actually have 9 operations of your quantum computer. So the other important question that our group may have addressed is that in a quantum information system, people are thinking of photonic channels because photons move very fast. They don't interact much with their environment, but they're difficult to store. So you store the information in nodes of atoms. So then the this atom photon network has the problem that you need to address. That's of information transfer. How do you transfer the information from your photonic side to the atomic one, and from atomic to the photon without knowing what the information is? Because remember the peculiarity of quantum mechanics, the moment you measure, the information goes away, it becomes a classical two-state problem. We have also worked on this a bit to talk about how slowly can we turn off on the control field, what's the impact of spontaneous decay, etc., etc. It's an adiabatic transfer problem, transfer of information from photons to the memory and retrieval of the information from memory back to the photonic channel. So there's a lot to be done even here. So I just end by going back to what Tanushree was talking about. The nomenclature varies a bit. Some people call the first quantum revolution is the 1925 one. I call it the 08th one. So the first quantum revolution enabled lasers and transistors based on the rules of quantum mechanics. The second quantum revolution is what I described, that aims to control quantum systems. So quantum technologies today seek to use quantum phenomena in computing, communication, sensing, metrology to go beyond what classical systems can do. So this has been part of my journey. And you'd ask me the question, then what's the next revolution? So there's a lot of startups. Umesh talked about it. You're familiar with the international scenario quite a bit. That it's industrial application is something National Quantum Mission is looking at. So the third quantum revolution is likely to be led by commercial innovations in cybersecurity, eco-materials, medical advances, etc., etc., etc. So my plea is that we need to make sure that these advances do not reproduce and accentuate the current inequities in the society. Any new technology, likelihood that it would actually get into the same inequity that I talked about in the first part, and our unsustainable ways. Because remember, the UN SDG goal number 5 was to bring in disparity. So every time you get into something new, you need to remember that our goal is to collectively prevent this from happening. Moral of the story: physics evolves when theory and experiment go hand in hand. Offshoot of this evolution is useful applications, quantum computing being one I talked about today, and scientific methodology, the way we do, is the gold standard, because that has led to these unthinkable advances, the counterintuitive advances in quantum mechanics that we see today, that makes the distinction between astrology and astronomy, for example. And I think that is the gold standard. One day, would you think that all scientists would be jobless because everything that is to be proved has been proved? I don't believe that. Methodology is such that it would actually lead to extension of the knowledge frontier and refinement of that knowledge. So I stop here, hopefully on time. So thank you very much for your attention.
That is called a good administrator. How can you stop right on top? I don't know. So questions, comments from the audience, please. Yes, please.
Yeah, lovely.
Thanks for a very wonderful talk. And it was kind of really academically satisfying to hear about the Gauss-Mandel effect right from you. I just want to ask a small detail, which I've always been wondering. You said that this was the first experiment which disproved Dirac's statement, whatever he made. Can you just elaborate on the experimental setup that you created? Because you're one of those rare people who do both experiment and theory. So I was just wondering about
these stories people are talking about now. I've given interviews in a French thesis where much details, maybe I'll share with you the details. When we came up with this idea, people were working on parametric down conversion already. But if you look at my paper, including Mandel's, he was interested in finding out how simultaneous are those two photons that are coming out of the fission. So even the home paper is actually not about quantum entanglement. It's about start-stop. What's the time difference between the two photons that were coming out? So when we posed this to Mandel, I was working on a sodium setup, and this setup was I mimicked it more or less. And his first reaction was, "Oh, you're talking about white light interference," You don't know. The reason I'm saying this story is that I did the theory first. 1986 was the theory where we worked out to show that this is possible. And the setup was kind of primitive. The Hongo manual was taken from Maryland Alice Grove, where you are playing with polarization. Mine was just a spatial interference. So two beams were physically made to overlap. I had a very sophisticated detector that I built myself. So yeah, it had to be done, and I can share the design with you later. And that took me more than a year. This experiment had taken 2.5 years to perform from beginning to end. So it's a simple one. Split the photon by doing the simulation to know which angles the photons would come back to. Just make them overlap through two mirrors, actually long infrared mirrors, and as a scan the detection plane by very special detectors that were thin, but they were at their spaced at L/2 of the interference range. So I was picking up more.
Umesh.
Very nice. Talk.
Thanks.
Really enjoyed it thoroughly. Is it possible to pair two photons? Not up conversion, but two photons forming a bond pair, possibly with opposite momenta and stop there.
Yeah, very good question. My materials colleagues are actually trying to do that. And so that's again going back the other way. You know, in optics people, we look at what happens to the photons. They would look at what happens to the material. And these kind of qubits are being talked about in various systems. So neutron atoms being also a very good candidate, not necessarily two photons, but then two spins that has been done. But for most of those systems, you need to cool it down substantially. I believe in these systems because you don't need to do all that, and field, deployment may be easier with these. But that's a matter of opinion right now. Nobody knows for sure. But yes, the answer to your question is yes.
Are there further questions? Yes, please.
Thank you, ma'am, for such a wonderful talk. I missed the point where you were explaining how EIT leads to the storage, ma'am.
Yeah. So EIT, I showed the dispersion. Do I need to get back, or do you remember the curve? So I can actually slow it down, right? I can slow down the light inside substantially. Now you can get it to the point where it actually stops. So incoming light, I had a nice video, but because of time I didn't show. Light comes, the information gets coded in the atomic spin, and then I turn off the control laser. So it stays within the Raman concordance time, of course. And then I turn on the control laser, then it comes out. It's that simple.
Thank you.
I think the last question from Prashant, your junior.
Yes.
Yeah, this always, amazed me. What was the difficulty you were facing in India? Because you came and quantum optics were doing so well. What was the difficulty with experimental?
First was actually there are two things, and even today I think more or less is there. We have got funding for specific missions now. At that time, funding for projects that didn't speak the regular language in India was a problem. I was speaking a very different language. Nobody in my committee understood what I was trying to do. That was the first problem. Second is that for these kind of experiments, we are all trained physicists. I learned experimental techniques in Rochester and other places, Columbia also. But I needed engineers. The reason I did so well in the French project, and Sipra understood that, because in my French lab, I have trained engineers to do it. I just have to give them the drawing, saying, I don't have to spend my time doing it. Tell them do it. And that every summer, of course, Delhi heat was terrible, so I was escaping Delhi heat. But I was actually going back on my Sipra projects where by email, I'll send the designs, at the time, even hard copies actually. By airmail, I'll send the designs. They would be ready with my setup. By the time I come in those 2 months of summer, I actually could do it. India needs that support. Scientists cannot be plumbers and electricians all the time. And high-tech plumbers and electricians. I did that all my life. I mean, this is ridiculous. You fix something, something else breaks down. Of all the places here, only Pune had the right environment. They made enough of their students into going into startups even at that time. So you had a technical backup. Our scientists don't have the technical hands to help them, and that's a big problem for experimentalists.
So
Just to
on
say
those-
that even workshops are not there.
Oh,
most
yes.
of the labs.
But even, some we could build and I could run it myself, it's not a problem, but you can't do it on your, when you are a faculty, you're teaching.
You have to make simple things like you have to go and use lathe and do those kind of workshops are not.
That's coming up though in India. That has changed if you will visit.
In fact, secretary has said we can prepare a list of recommendation and it is nothing to do with gender.
Yes,
But this is the need if we really want to push our quantum technology, because the government is talking about technology, not even science. So we can make it a part of
Sure.
our recommendation. So on that note, thank you so much, Rupa, for very exciting talk. And now I hand over the mic to
Just a minute.
the second section chair and before that organizer has to say.
So I would like to request the session chair to kindly give a memento to Professor Rupanjari.
Yes. I forgot. Thank you. It's a real wonderful.
Thank you. Thank you, Professor Das Gupta and Professor Rupanjari for these. Now to chair the second session, I would like to invite Professor Umesh Wagpal.
Thank you. We are almost back on schedule, only 5 minutes delayed. In this session, we have two talks. The first one has 40 minutes of presentation and followed by 5 minutes of discussion. And the second one with 20 minutes of presentation followed by 5 minutes of discussion. The first speaker is Professor Shohini Ghosh. She is a professor of physics and computer science at Wilfrid Laurier University, Canada. She was the president of Canadian Association of Physicists in 2019 and 2020. She is the director of Laurier Center for Women in Science. And in 2020, she was selected as the INSERT chair for women in science and engineering. It's a pleasure to have you, Professor Ghosh. She will talk to us about sensing the invisible, a quantum perspective.
Thank you. It's really very special to be here because, like most of us, I do a lot of talks at conferences, but this one is truly unique because, I'm a daughter of Kolkata. I spent my childhood here, and now I get back to the place that I love to talk about a topic that I love, quantum, and for this very special occasion, talking about this other topic I love, which is women in science. So I'm really happy to be here. So there's one more thing that I actually love, so I wanted to share with you, and that's, superhero movies, like the Marvel movies and all, the whole series of them. Is there anybody else who loves those? So, these movies made me always think, what oh, I think I'm having a little bit of an echo.
Maybe you could go.
Yeah, maybe I'll go up here. Is that better?
That's better.
I wondered what superpower would I like to have? Anybody wondered that too? If you could have any superpower, what would you have? And then I realized I actually already have one. And my superpower is invisibility. Often in my classrooms and other, work environments and in many, many situations, I think a lot of you might also have that who here thinks they have that superpower occasionally? Yeah, I think we do see that a lot. And I want to tell you that actually all of us women in physics, at least, seem to have that superpower. I'm going to show you. We can do a little bit of an experiment. I did this before I got here, but you can feel free to do it on your own, actually. All you need is take out your phone and do a Google search. So here's the Google search. You can try it now if you like. I guess you can't quite see it, but the search is just search for famous physicists. I don't know, it's going to be different if you do this search. I did this back when I was preparing this talk in Canada and on the flight. So I don't know if it's different if you do it in India. I don't think so. But you can try if anybody wants to. Pull out your phone, do this search. Here's what I got while you do your search. you get this whole series of, images. It looks very beautiful, and you can scroll more. So I scrolled. That's what you get. And then I scroll some more. And then I scroll some more. You see a pattern here? So this to me is kind of the evidence that even today in 2024, there is of course this strange deletion of some physicists in favor of others, and even, AI has learned it because that's what Google is basing all of these results on. If you do, okay, before I go to this, if you do another search for famous women physicists, try that. I'm not going to show you the data, but if you do that, you'll see that Google knows a few names, but doesn't know to include those in this bigger context of who is worthy of that visibility and who isn't. So this is actually important because, of course, within our community, we might be aware of this issue, but in the broader context of society, actually, this is the primary source of information. We know this. When we talk about where do biases and perceptions of what are the roles of men and women in society come from, this is the primary way that these are developed and confirmed. So it's really important to have to think about how we can address these going forward. And I'll give you one more example, which is kind of shocking from, in Canada, actually, back when Donna Strickland, who's a good friend and colleague in Canada, she became, the Nobel Prize winner in physics in 2018. And that was quite celebrated, of course, even more in Canada because she's based in Canada. It was all over the news. And then Canadian CBC, which is a Canadian broadcasting corporation, did this poll to ask Canadians to name a woman scientist or engineer after she won. And as you can see, half couldn't name anybody, leave alone her name. So there's another aspect to this, that is that it's not just us, having women who are very successful. Even when they're celebrated, there's another layer of bias happening where we almost expect to forget them because we don't include them in our histories. So even really well celebrated women don't register. And that's really a big issue. So, seeing these kinds of examples, I mean, of course, personally as a physicist going from India, then I did high school in Singapore, then I went to the US, did all my schooling there, and then ended up in Canada. And very similar to what you heard from Professor Ghosh, I certainly started noticing this huge gender issue much more in the US than before that. And Kolkata, I was in La Marche, which is a girls' school. I think that was an important reason why I did not really think about these issues until much later. But when I was in graduate school, and this became obviously an issue, almost every week I started realizing that I was thinking of quitting. And I don't, because there was that isolation, there was this constant feeling, am I supposed to be here? Am I good enough? Do I have the skill sets? And I didn't, luckily, but I was always trying to find that reason to stay. So eventually I thought, well, I'm a scientist. I'm trained to think about data. I'm trying to think in a scientific way. So I'm going to ask this question scientifically. What's the evidence? Do I have the skill sets or not? Somebody else must have tried to figure out whether there's a particular skill set associated with a particular type of person which makes for good physics. Do I have the skill sets or not? And of course, this is very much related to these ideas that I think all of us are raised on, whether explicitly or not, that, yeah, of course, girls play with the dolls and boys are the engineers and they can build things and, they have those skills and somehow those skills are what are needed. So therefore, boys are really naturally skilled for this. Well, why not test that? That's a hypothesis. Let's test whether boys have that skill or not. Turns out there's lots and lots of such data. Lots of studies have been done. Even from early days. So if there's an actual biological difference and boys are somehow naturally better at this, you should be able to see it from an early age. So this is one example of the kind of studies people have been doing for a long time. In this case, it's about early childhood development, where they just tested to see how well could girls versus boys count. And we're talking about 3-year-olds. So it's not very good that it's, everybody can count till 2. And then, after 3 or 4, it's all bad news. But there's no difference really between boys and girls. And there are many, many studies that confirm this. And it's not just at the early childhood rate. You can then think, oh, well, maybe over time there's some differences. And boys acquire those skills better than girls in some way. That too is testable. Because you can study what is the performance of boys versus girls as they grow up. And this has been studied not just in US or Canada or India, it's been studied worldwide. In fact, there are even standardized tests, which are not ideal, but they're some kind of way to assess what's happening around the world in terms of learning and development. So here's, for example, tests done in the OECD countries. I know it's a little hard to read, but this is really just showing the data presented in the form of whether boys perform better in the standardized science test or do girls perform better. And it's organized by countries. Now, if boys were actually naturally better, you would expect basically the bars would be basically above the horizontal for everybody. So that would show boys are generally performing better. That's not the case, and these kinds of tests are done every single year around the world, year after year after year. So we have decades of actual data that prove that there is no consistent performance indicator that boys are better. In some countries, girls do better, in some countries, boys do better. And it has a lot to do with the context, the learning environment, and things like this. So that's how much data we have. This is nothing where we need to do more studies. There is no doubt that there is no evidence at all that there is any difference. And yet, this bias that you saw in those early, whatever the Google searches, and you can do many other searches, and you'll see clearly in front of you all of the biases that we have adopted. They're still there, embedded, entrenched, no matter how much this data is telling us the opposite. There's data also for India, for example. There's these tests of achievement. This is in mathematics, and the blue is for boys' performance doing better. Girls is the orange, and equal is the light brown, I guess, here. So you see that it's kind of randomly distributed. And similarly, if you look specifically at science, not mathematics, you see something else there. So there isn't really any way for us to justify this constant bias. It's time to move beyond this. And that to me was good news, because it means that it's not, if it really were biology, then maybe I would have quit physics because I'm like, oh, well, I don't have the right chromosomes. But luckily, all this made me say, yes, I can stay, I can do this, because there's no reason for me to leave, not biologically. And then you look at these, the reality is that, of course, there are still differences in how we are seen as scientists, but also actually there are differences in performance of women. Even in classrooms, there are differences you see sometimes, but it depends on whether or not there's a strong bias against girls or not. So that's an important piece to keep in mind. There are other biases and other influences. So for example, there are differences in how boys grow up and how girls grow up. That's of course true. This is a very famous test where some researchers observed in a science museum how parents were talking to their children in the museum and how they were explaining all the science. And what they found was that when the sons asked questions, both moms and dads would spend a lot longer explaining the science to the boys and not as much time to the girls. So that's what's shown here, that this is the time, percent of interactions with the parents as they explain. This is for the boys and this is for the girls, both for dads and moms. So there's a significant difference. And it's not because the parents don't love their daughters. They didn't even realize they were doing this. This only comes out when you actually study all the data and put it together and you say, oh, this is what unconscious bias is. You can measure this. It's a real thing. It's not just somebody's opinion. This is absolutely something that, because you can measure it, you can figure out how to fix it. So to me, even this is good news, because this is behavior, and behavior can be changed. So I'm, as you can tell, I'm quite an optimist about these things. Here's another very, very famous series of experiments trying to figure out what do we see as scientists? Who do we imagine? If somebody tells you, draw a scientist, what do you do? Well, this is what they ask kids to do around the world, right? Kids of all ages, and this has been done. Hundreds of thousands of kids around the world have drawn scientists as part of the study. What do you think they draw?
Man in the lab coat.
In a lab coat, of course. So, and there's actually a very specific idea of that man. How the man is drawn is actually very, very, very uniform. Wild, crazy hair. So I went through lots of these. They're really quite entertaining, and I picked out a really good one for you to see.
That's the Einstein.
It is the Einstein trope. And in case you didn't, I guess the person here wanted to make sure you knew, because they even helpfully put the equation, which at least is good because they know their science. It's correct. But yeah, this is what most kids draw, because that's, it's not because somebody told them this is what a scientist looks like. It's what we start absorbing as unconscious bias. And this is boys and girls, by the way. Girls tend to draw other women scientists more, but still pretty low. And over the years, women scientists are being drawn more and more, but it's very, very slow. But here's what's interesting. You can actually take this kind of data, as I said, it's behavior, right? So there are lots of experts in behavior, psychologists, social scientists, and you can do tests and experiments, kind of like how we do in the lab too. So one experiment was done where this teacher did a draw a scientist test with her kids. They drew the standard things, and then many, many weeks later, just so that there was enough gap, and so that there was not really a correlation, she invited a scientist to speak to her class. And the scientist was a woman, and she didn't wear a white lab coat. She didn't talk about being a woman. She just talked about science, and she wore this multicolored kind of outfit, and just was a really good at explaining her science. So the students loved it. And then many weeks after she left, they did the draw scientist test again. And look what they drew. It's amazing, isn't that? That's what I mean. It's good news in the sense that we can change. Humans are adaptable. In fact, we're very easy to manipulate. So maybe we should use that, in the right way to move to a better kind of set of ideas about who a scientist is. So given all of that, there's also very, robust data around actual specific challenges that we can change. None of this is not changeable. This is why, although we talk a lot about challenges, it's important to frame it as the challenge. There's a reason we identify the challenge, to be able to fix it. It's not enough just to stop at, okay, these are the challenges. All of them are fixable. So, and this is a huge data set in physics. You can look this up on the American Institute of Physics website. There's lots of data and plots of over, I think something like over 100,000 physicists have participated in surveys. And you see that you have what you would expect. There's less access to resources, all these challenges, more time for housekeeping and child rearing work, and also elder care these days much more. And slower kind of advancement, things like awards and access to funding and giving talks, invited talks, all of that is in there. Not really surprising, but why can't we fix it? If we know that there's not adequate resources, we can make policies to change that. Policies around hiring, policies around promotion, these are again fixable, is what I want to say. And of course, the most important thing is, given all of these challenges, the survey asked, why do you stay in physics? They asked both men and women. And that's the one thing where there's no difference. What do you think the answer is? We love it, of course. So that's really, again, I think important to keep in mind. That's certainly why I ended up not quitting. So the other final good news I want to share with you, certainly for me personally as an inspiring story, is that there are absolutely throughout history numerous stories of women who have contributed in big ways. And I want to tell you one such story because we're talking about quantum, but she's not actually in textbooks on quantum science. She's now known more on the astronomy side as an astronomer, but she was an astronomer. Cecilia Payne-Gaposchkin, but she really should be listed in that list of amazing contributions in quantum, because she was one of the earliest scientists to apply those laws of quantum science. And there's a direct Indian connection. So actually, she was a PhD student at Harvard Observatory. She was the first PhD student there. And what she did was, using all of the observations, the spectra that they were collecting at the observatory, she was able to apply early quantum theory. In fact, Meghnad Saha's ionization equations. He applied them to all of that data and figured out that all the stars were composed of hydrogen and helium. Nobody really believed her at the time because it seemed really strange. People were assuming that the sun should be very much like the Earth, for example, in composition. So why would stars be so different? But eventually people came around, and her thesis was considered one of the greatest astronomy theses ever written, but it's really quantum at the heart of it. She did, she finished her PhD, of course, did not get a position there because Harvard, even her PhD was not from Harvard, it was from Radcliffe, because they didn't give PhDs to women in Harvard. She didn't get any kind of official role. She continued as an assistant at Harvard, not even an astronomer, not even a researcher. She taught courses that they would not list on the books. So that went on for years and years. Eventually, I think something like 20 or 30 years later, they finally got around to making her an astronomer, and she went on to become the first woman chair of any department in Harvard. So she's kind of one of these inspiring role models for me personally because of that quantum connection and the India connection. So she was studying, of course, the largest objects in the universe. For me, I tend to focus on the small, which is what we do now, of course, in quantum computing. So I guess in the remaining part of the talk, I want to tell you more about some of the work I did. And now I sort of balance work towards addressing all these challenges now that I can think of it in a scientific way. I spend a lot of time creating actions and initiatives to address those barriers in a way where we can fix them. But very much based on, here's the evidence, just like in science, here's the data, here's what it means, here's how we can improve our experiment, and then let's test again and fix again. So that's what we do in our Center for Women in Science to address some of the challenges around hiring and, for example, or funding and many other aspects. But at the same time, in my own research, inspired by women like Cecilia Payne, I've been focused in quantum information and quantum, actually initially quantum optics kinds of research, and now more applying that to quantum information and quantum computing. So one of the early experiments that I was involved in, although I'm a theorist, I worked with some colleagues to make these images the first really clean experiments to study a very foundational question in quantum, which is to do with this idea of the quantum classical boundary, as you heard again, where we were trying to figure out how big or what scale of system you need in order to see something like chaotic dynamics, which is a very classical effect. So this idea of whether there is chaos theory impacting quantum systems is actually an open question. It's one of the questions, again, pointed out by Einstein, that hasn't really been addressed yet. It doesn't get as much attention as EPR, but it's actually as weird and mysterious because we don't understand that path to classical chaos at all. There is no parameter we know to tweak to really get there. There may be a whole combination. So that to me was a very interesting foundational question. And it's very hard to do experiments on this because you have to somehow figure out how to control a system, change its scale, understand how chaotic behavior emerges. But chaoticity is all about sensitivity to initial conditions. So to control it and not just have everything washed out in experimental error is very hard. So this was one of the early experiments that I was involved in, involving cold cesium atoms. This looks like just some computer rendering, which it is, but it's actually a rendering of actual data collected in the lab of cold cesium atoms, showing the probability distribution of the hyperfine spin, which is nuclear and electronic spin of a single cesium atom. You can control it, you can initialize it and then watch its dynamics and take sort of snapshots of this cesium atom over time as you control whether or not it's regular or chaotic behavior. And then if you put enough snapshots together, you get a movie. So we made a movie, and here's, oh, there it is playing. So this is a movie of the cesium atoms probability distribution. This is actual data showing it sort of evolving on, it lives on this spherical phase space. So that's what you're seeing here. Details not so important, but what was really amazing is we could see this regular behavior, and then when we changed it, I don't have that movie loaded. It was the file unfortunately has an issue with it, but you can actually see completely different kinds of behavior. So you could see actual signatures of chaos in individual cesium atoms, which is what we would consider a very quantum system, and yet here are signatures of chaos. So that was something that to me was, it went back to this question of invisibility. Here was a way that we see things that are invisible and finding unexpected outcomes. Now, over time, these experiments, these foundational experiments are interesting because they tell us more about quantum, but now they're of course connected to actually building real quantum technologies like quantum computers. So this is an image of, very nowadays you see this everywhere, right? This is the famous chandelier quantum computer. This one is IBM's, but typically all these superconducting based quantum computers have this sort of image. Most of this, of course, because it's really the cooling system you're seeing, the refrigerating. The chip is somewhere at the bottom of this. And it takes a whole room to control these quantum computers. So we're talking about systems that are early stage technologies, really. It's not like we're going to be able to do very large scale, robust quantum computing as yet. But to me, it was really an interesting system because I was still thinking about how can we take these chaos experiments. To me, it's about the foundational science. So I wanted to know, can we use these quantum computers to do simulations of these kinds of chaotic systems, even if they're not perfect? Is there a way to go beyond what we've already done in experiments in the past? So the experiment in the past was actually things that I'd done right after my PhD in my postdoc days and early sort of faculty days when I just started. And so years later, here I was able to think about building on those experiments, seeing if we can explore a greater parameter regime with these new quantum devices. And turns out that you can. So I don't like this. You can't probably see the images very well here, but the main idea here is that you can create an actual code that simulates a chaotic system. So a series of gates that will actually simulate the evolution of the system according to a chaotic Hamiltonian. And what's good about it, in terms of just writing it as a series of gates, a gate is programmable, meaning you can change the parameter without changing the gates. And that can allow you to put in the right values of your gate to go from very regular regions to very chaotic regions. And we found this clever technique where, because it's basically a simulation, you can find the set of gates that you can that will simulate your system for any length of time without really breaking. So we have a constant gate set that can actually be used for any length of time. So we could do these long-term quantum chaos evolutions. And what this plot is showing is you want to see how well it's doing, meaning is the fidelity high? Because you don't want decoherence to wipe out all of your data. And here you see that for a lot of different parameters, you get, if you zoom in, you see some oscillation of the fidelities, but no matter what parameters you put in, you get pretty good 90% and above fidelities in this kind of simulation. So this was one of the early studies which showed that even quantum computers of today they can be useful, because we couldn't do this in an experiment before. So that was useful, and we were able to explore regimes that had not been verified in experiments before and confirm a lot of the theory done that way. So that's really exciting to me, that it took such a long evolution to even get to this point, and who knows what we can do with even better quantum computers. And once you start exploring these different regimes, we actually accidentally found this really amazing new effect that we're trying to model the system to have the theory and to test the experiment against. And because we were looking at new regimes with different parameters that had not been done before, what we found was that there were particular parameter values. I won't go into the details. This is a particular system called the quantum kick top. So there's a kicking parameter in the top. And if you fix it at particular values, strangely, no matter how much you scale up the system to make it as classical as possible, meaning you take some quantum number and take it to infinity, no matter how big you make the system, at particular parameter values, the system starts becoming, it wraps around because it's a spin system. So it's always evolving. It's basically a momentum vector rotating on a spherical surface. So if you're very clever, what you find is that the average spin vector actually after a few driving kicks will just come back to itself. So it won't become chaotic and it won't ever match what you expect classically, no matter how much you scale the system and make it really macro. And so this challenges this very, very foundational idea of Bohr correspondence, where we sort of roughly hand wave and say, okay, if a system becomes macro rather than micro, it'll behave classically. This was sort of this unexpected effect where there are certainly other examples where you can engineer a system to remain quantum, but we were not trying to engineer it to remain quantum or do anything special, just on its own, just by changing a parameter over a range at one particular range, it's almost like a resonance. It just stops doing what you expected. So this was very strange. I still don't understand it. We can write down the theory and prove that that is correct, but we don't really understand what's happening there. So that's always fun when you find something that is strange. So that's part of what we've been exploring recently, but I've also been exploring a larger set of questions related to quantum information theory beyond this question of chaos and correspondence. So I'll give you a brief taste of the kinds of questions we are exploring. On the quantum communication side, what we are thinking about is, what if we had a network of quantum connected particles, multi-qubit entanglement across many, many different nodes. Now, this is of course not something that's possible today, but then we're doing the theory to try to analyze it. So I think a lot of people have heard about standard quantum teleportation, where Alice can teleport a qubit, quantum bit, to Bob without actually sending the parameters of the qubit, separating out the classical and the quantum information. So a variation on that, when you have more than two qubits, not just Alice and Bob, let's say you have Charlie, you might have even more players in your network, but the simple case is 3 players. You can ask what kind of other communication protocols can you do? And one of them is kind of like this permission protocol where Alice still wants to teleport to Bob, but Charlie is controlling it, meaning remotely, so that without Charlie's permission, Alice can't send to Bob. And you might say, well, why would that be interesting? Well, there are various scenarios where maybe there's passwords you're trying to share, or there's some, some other reason why there needs to be control. Maybe it's a spy network, who knows? But there's reasons for looking at this kind of a scenario. But on a foundational level, it also tells you how entanglement can actually be used to transfer information or stop transfer of information. So that's kind of what we have been looking at, and we have this new measure to try to quantify what is this amount of control that Charlie has. Can Alice and Bob cheat and still teleport, or can they be stopped? What's the kind of entanglement you need? What measures you need? So there's all kinds of different types of entangled states which give, and different scenarios of all the tasks that you can do. Or I guess this one is not working. That's okay. These plots are basically all the different types of different entanglement you can use. And so that's something that we're exploring now more and more. I guess I could you forward it or just on. Oh, I could do it here, right? So here's another area that we've been focusing on, which is on quantum optimization, which is actually one of the more near-term real-world applications maybe that we could do, because you don't necessarily need the full-scale quantum computer, universal gate set to do one task, which is optimization. So one of the approaches to optimizing a function is to use this idea of quantum annealing, which is not something, I mean, it can be mapped into what would be called adiabatic quantum computing, but it's related, it's not the same thing. Again, don't have time to go into the details, but because we're talking about one specific task, which is optimization, and one particular approach, quantum annealing, that's something that can lead to pretty interesting and useful kinds of applications if your device only does that. So one such device is built by this company D-Wave that you may have heard of, and luckily it's based in Canada, so we have access to that device. And so we've been looking into how can we try to find solutions of difficult optimization problems, large multiple parameter problems, and we find there's this one problem called trying to find a particular special type of matrix, which has certain properties related to determinants, kind of like with permanence also, but I won't again go into the details, but it's a hard problem. And what we've done is found that this is better done on a quantum annealing device, which is the D-Wave. If you have large, not even that large, we're talking about matrices that are about 20 by 20 in size. So even that, if you run it, yes, you can find the answer on a classical computer, but it's going to be better on a quantum. And at values of 80 or more, or over 100 by 100 matrices, turns out these are actually, we don't know the answers to that. So we're already getting to a point where we can do real world problems. Similarly, we're looking at traffic flows of data, in information flows in telecom networks, trying to find optimal solutions to that. So that's kind of interesting real world work that we've been doing recently. But as I mentioned, I'm also focused on using scientific approaches to gather and assess data, not just in quantum, but about us quantum scientists and physicists. So we did this recent survey called Canadian Physics Counts. And that's basically a survey of all the physicists in Canada. We didn't get everybody to participate, but we got a very large number who did participate in the survey. So we could gather some data, not just on gender, but this was a very, very large set of questions on gender, race, disability, career level, income, many aspects of identity, all of which does impact who gets to be successful and who doesn't. And we found some very interesting results. The paper is online, and this allows us to then build, recommendations and guidelines for how to do better. So I feel like data has really helped us drive that conversation in Canada, at least. So that's a taste of the kinds of things that I've been working on the research side. And very recently, I've also had this opportunity to be part of building out the quantum ecosystem in Canada. Like India, there's a national quantum strategy in Canada, and each of the different provinces also is now building out their quantum ecosystem. So I'm involved with the Quantum Algorithms Institute in British Columbia, which is where D-Wave is located. So now we are working with many companies there. Another famous company based in British Columbia is Photonic, and there's a lot of small startups. So there's now this drive to connect all of these companies that are building quantum devices to potential users of these devices, such as telecom companies or healthcare and things like this, and connect them also to all the universities in the area. So this is a three-way thing which the government is funding to build out that ecosystem. It's probably quite similar to planning and strategies happening in India. So it would be quite interesting, of course, to exchange ideas and see what's happening relative to each of the different countries out there building this. So that's been quite interesting. It's growing and very strongly. And one thing we're now focusing on, based on all of this data that we've collected, is that we do have to focus on things like not just what technology is being built and who's going to use it in terms of these companies and use cases, but who are the people in the ecosystem? Does everybody have access? Are we going to use it responsibly? What are the regulations and policies? And how is it going to be inclusive? So as part of that, we have just launched this thing called the Center for Responsible Quantum Innovation and Technologies. And our hope is that in the next round of the federal budget, there will be funding for quantum technology, but also for this kind of work on diversity and inclusion. So we do have a long way to go. The private sector is really growing, as you know, it's heating up. There's always a race happening. And you may also know that now there are companies that are fully just quantum-focused, quantum computing companies that are now publicly traded on the stock market. The very first one of them was IonQ. A couple of years ago, it already went on the stock market. So I went and looked up their leadership. And this is what I have. So we have a long way to go. And this is something that feels like a big challenge, but it's an opportunity, isn't it? This is a new time. This is the start of a revolution, the second quantum revolution. So we can maybe use that to say, well, let's make a revolution that's much better than any of the previous revolutions we've ever had in technology, because it shouldn't just be a technology revolution. It should be a social revolution at the same time. Wouldn't that be amazing? So on that note, I'll leave you with a more inspirational photo than the last one. This is a photo of a conference that we held in Waterloo, which had representation from 52 different countries. And these are all physicists. So this could be what drives the next revolution. So I hope that's the revolution we will build. Thank you.
Any more questions, comments? Yes.
I'm just curious to know about your opinion. For example, I think Rupa showed a quote from Shankar Das Sharma's game that it's a big hype. So since you work on algorithms and quantum algorithms, so it is kind of acknowledged that only specific algorithm quantum computer will be actually effective. So can you make some general comments about what class of problems can be dealt with it? Of course, you showed the example of chaos, but
Yeah.
any other thing in general?
Yeah, so I'd say that, of course, the really big one, which is why everybody is racing towards, is, encryption or at least decryption. So factoring and that set of problems associated with the quantum Fourier transform. So if you can use quantum Fourier transform in any algorithm that you develop, that's going to give you that exponential speed up. Currently, the main such application is decryption. But that's big enough on its own that even if we never do anything else with the quantum computer, it will be enough. But I think there is more we can do. Some of it I agree is high. That we don't have any rigorous proof, for example, that quantum can actually help with things like machine learning, which there's this whole quantum machine learning happening because, of course, AI is taking off. But it's clear that whenever we talk about big data, we need to figure out a way, for example, it's not enough just to do the calculation on the big data. Maybe you can find a quantum algorithm to do that, but you need to first map the classical information into quantum, and that's a huge data set. So unless you figure out an efficient way to do that, that's going to be a big bottleneck. So there's no rigorous proof that machine learning will have any benefits. Some people claim otherwise, but I'm not in that group. Quantum simulation, meaning things like, basically chemistry. So being able to solve, Hamiltonian, right? Ground state energy, things like this, I think is absolutely feasible. There's some really interesting work showing that you can use quantum annealing techniques to do that, and already showing performance improvements. Again, there's no rigorous kind of proof, but I think that's going to be quite successful in the near term. Long-term, large-scale, robust, quantum error-corrected computers, I think we may have, applications that we haven't even thought of as yet. But I'd say the big ones are, of course, if you had to pick an area to focus to develop algorithms, I would look at quantum Fourier transform and that class, and think about that, or simulation, and think about problems that you can do there. And I think quantum annealing has been sort of dismissed, but I think it's too early to dismiss, and I think there's lots of potential.
Thank you.
Is there any other quick question?
I'm
Hi, so if you go to that, the slide where you were showing this, chaos, transition. Yeah, as it's the movie that you showed, so can you, so I just missed it, can you tell me like, yeah, exactly. So what is it? It is the,
Oh, this the
and
actual.
the experiment, can you just quickly, yeah.
Yeah, so the experiment was to be able to, we do state tomography of the hyperfine spin of cesium, which is the nuclear plus electron spin. So you can actually, prepare the hyperfine state in a particular initial state. Actually, you can do any state you want, because it's just, it maps onto just being able to rotate to some particular location on the sphere.
Yeah.
Right. And then you apply your Hamiltonian, which is this kicking Hamiltonian using, magnetic fields, as well as you use the Stark's effect to control the Hamiltonian. And so then you allow it to evolve according to that Hamiltonian, which is chaotic. And then at the end, you do state tomography. So you measure the population of in each of the spin levels. And then you have to do it, of course, on many axes to get the full state, reconstruct the full state. And what's being shown here is once you have the full quantum density matrix, you can convert it into a quasi-probability distribution. In this case, it's called the Husseini distribution, which is just a mathematical mapping. And then we map that because then you can think of it as a probability. And that's what's being plotted.
So where is the chaos transition you are talking about
Can
here?
we take this discussion on
Yeah,
the
later,
break,
we can
please,
talk.
because I think we are running out of time. Sorry, we move on to the next one, but before that, I have a pleasure to hand over.
I would like to request Professor Wagmari to begin.
So the next presentation is by a brilliant experimentalist, Professor Dhavala Suri, who just joined IISc last year as in the Center for Nanoscience and Engineering. He's an assistant professor. Dr. Dhavala Suri is famous for making her own instruments, as I have seen in many places. Pleasure to have you.
First of all, thank you very much, Professor Sahadas Gupta, for this invitation. It's an absolute privilege. And yesterday or today morning, Vandana was asking me it's my first time in Kolkata, and then she said, "How? You're a scientist." Coming to the science city of the country and also being part of this very special occasion is of a lot of privilege to me. The second thank you is to all of you here, because you all have made so much noise and so much effort for people in my generation, things are better. And it comes with a lot of gratitude to everyone here, as well as those women who are not here as well and have made a lot of contributions to women in science and technology. And it also comes with a lot of responsibility, looking up at you all on what needs to be done to keep the whole ecosystem balanced. My talk today is going to be on the activities that go on in my lab, which is at its infancy right now, at about 8 to 9 months. And there's a lot of, like Professor Wagmare said, right now we are just building a lot of things, right from small toys to big equipment. A lot of building is going on. And but the scientific problems are centered around topological insulators, superconductors, magnetic semiconductors, a class of all this class of materials. I'll pick one or two topics and discuss the scientific interests that drive the research in our group. All right. So we do synthesis of these materials using a technique called molecular beam epitaxy, and this is really a very special technique of synthesizing materials, where you can. I'll come to the details of this. But something that interests me and hopefully my group members is what happens at the interface when you have two different classes of materials. Fine, there's material A and material B, but when you put them together, the Hamiltonian doesn't have to be A plus B, but it could be something totally different. So we often ask the question, what happens at the interface between the two materials? So I'll basically touch on a few questions like exchange coupling driven proximity effects, and then what is the effect of when you apply an in-plane magnetic field, what happens to topological systems or magnetic hybrids and superconductor ferromagnet systems. All right. The whole motivation, because this is a women and quantum tech sort of thing, is that, I mean, this is the actual picture of world's first transistor, whereas now we have come here in the same volume, we have so much. And this is really thanks to thin film technology, where humankind has understood how to go from bulk and then sheets and foils, and now one transistor can be as big as just one molecule. Okay, so it's really thanks to that technological evolution where humankind has gone from there to there. And the future, I don't have to speak about this, everyone knows. The future is quantum, 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 all about it. Great. So what do you have to do to actually do this, or what can we do?
Go back the other way.
I hope I don't have a phone. Yeah. So all of this is true, but what can we do, or at least my perception of what can we do as Indians to catch up with the rest of the global race in this quantum tech is materials. And what we need is, for instance, when Professor Ghosh was talking, he was talking about this quantum optics systems where things are very easily, you write down the Hamiltonian. I'm sorry for being very vague, but write down the Hamiltonian, you can actually simulate, or you can actually get that system out there. And solid state system, welcome. It's just not there. But then ultimately your devices or your phone or whatever gadget is a solid state system, at least as the way we know now. Then there are two things. One is superconductors. These are materials that go to zero resistance below a certain temperature. And devices made of superconductors are presently what all countries are talking about in terms of when they say we made 1,000 qubits, we made 10,000 qubits or whatever number it is, they're talking about superconductor solid state qubits. But then just to remind you all, these are conventional qubits, and there is no, if we are talking about eavesdropping and what the quantum world demands, then conventional qubits are not yet there, and that requires topological systems to come in. And this topology is basically this class of is the field of mathematics, which basically looks into continuously deforming an object smoothly from one to another without breaking this property here, which is, for instance, here it's the hole, the number of holes is the same. You look at those properties, and if you can combine this mathematical property with condensed matter systems, perhaps we will get to that protected states and protected topological systems in qubits, and perhaps that's the way to go. And where are we lacking right now is material platforms. We don't have, we need extensive research on what are those efficient material platforms where this can be realized. We have a long way to go in this. Just briefly about topology in condensed matter systems. As I told you, topology is like, let's say you take all those objects which have absolutely no hole in them, put them in a box, and that belongs to one class. You take all those into which have one hole and put them into another box, that's one, and you can go on numbering them depending on the number of holes they have. That's called the topological invariant. And you do this, that's what topology basically does mathematically. But in a condensed matter system, for a condensed matter physicist, what does this mean? We look at the band structure and we say, hey, what's going on at the Fermi level? If there is absolutely no states, that's a trivial insulator, that is zero. Whereas let's say there is, if you see here, there's one state crossing from valence band to conduction band, that's one, and so on. You can have this band crossings as your quantification, and that is what topology means for a condensed matter physicist, and to realize this in a material system. But what is more important and what was so important was that at the boundaries, that is, let's say I have a topological material, if you have a zero and a non-zero class of topologies in a material system, then at the boundary, you have to break some symmetry to go from one to that, and that gives gapless edge states. And that is the realization of topology in condensed matter systems. And it's a very beautiful marriage of theory experiment in my little bit of exposure to physics, where theory predicted something, experiment showed something, and happily ever after, they got a Nobel Prize and so on, right? So Xu Chengzhang predicted this, Lawrence Molenkamp did the experiment and showed that, look, topological systems can be synthesized in a material heterostructure. Although the first discovery was the quantum Hall, which was demonstration of the property of topology, but when it comes to 3D topological insulator, it was this two-dimensional 2D quantum spin Hall oscillator by Lawrence Molenkamp. Now then the question was, can you have three-dimensional proper, not necessarily a two-dimensional electron gas, but three-dimensional one material, which is a topological insulator? Then, yeah, theory again predicted that, look, do this, this, this. That's where, sorry. Oh, okay. So theory predicted a set of things. And if you see, this is an angle resolved photoemission spectroscopy, short form for looking at the dispersion relationship of a material. You do DFT or you do band structure calculations, you arrive at E versus K in various forms. If you want to look at it in a material, you do RSpecs, and then you see here there is a bulk insulator, but at the surface there are these conducting states. So a topological insulator is nothing but this material where there is a separation, conduction, and various band of separation. So that's in the bulk of the material, whereas on the surface of the material, there is a conducting surface state. So you take a material, let's say this one, and then bulk is insulating, surface is conducting, then that's a topological insulator. Now, someone asked me, a small child, it was in fact a 5-year-old or someone who said, if I cut it, then like I take, like she asked, I take a piece of wood and then coat it with chocolate, and then I cut it. Can that be, topological insulator? Because you can take a piece of wood, coat it with metal, and surface is conducting, bulk is wood, it's insulating. Can that be a topological insulator? And she herself said, you cut it, then it's still, distinct. It's not one material. So it was really interesting. This was one of the outreach happy moments where a kid understands what's a topological insulator. So there are two ways. I told you about 3D topological insulators. There are two ways. You can take some spins, arrange them in a certain manner. That can also give topology. Here, the up spins are going in one way, and you see here the central spin is downwards. So from up to down is a very smooth, continuous deformation. It's not abrupt. So that's another way to realize topology in condensed matter systems. The way you synthesize these materials is something, there are many ways, but something which I specialize in is molecular beam epitaxy, where you can grow materials at the precision of monoatomically. You can pick those materials from the atom, periodic table, evaporate them in a very controlled way, where you can synthesize materials precisely like this with high epitaxy. And that slow rate of deposition allows for very many complexes to phase, complex phases to form, which would otherwise not form. And this is what we are building in our lab from scratch. And I'll quickly go to the interest that we look at, which is basically proximity effects, where let's say we have a topological insulator of some form, whatever it could be. Then we always ask the question, what if something else comes close to it, and what happens in the interface? So proximity effects is basically that field where you take a material A, B, C, then at the interface, the properties are totally different, as I said. An example, for example, is here this gold electrodes are superconductors, whereas here there is a thin sheet of graphene. And you see that the superconductivity has spread into the graphene, and it shows a nice IV curve of a superconductor, which is you are increasing current, but there is no voltage drop. That is the characteristic. So it's purely proximity driven. Graphene is not a superconductor, but it becomes so in proximity. And one of the questions we asked was graphene is really interesting because you have this graphene, now you put a magnet on top. Graphene has a Dirac cone spectrum, right? And then you bring a magnetic insulator on top, then what can the magnetic insulator do? If you want to realize quantum Hall or any topological states in graphene, you need extremely large fields like 20 Tesla, 30 Tesla, extremely low temperatures. One way to get rid of this is instead of applying really high magnetic fields, couple it with a magnetic insulator. You don't want a magnetic metal because then electrons would flow through this magnetic metal. So one of the works our former group did was you take graphene and then put a magnetic insulator on top. What this quantified was just the exchange coupling between this magnetic insulator and graphene can give rise to a field equivalent to 18 Tesla just because you have exchange coupled it and grown it in that precise way. You don't need extremely large magnetic fields anymore. And now we started asking the question that what happens in the same system if I have a topological insulator, not just one layer of graphene. So this is where we looked at this interface of a topological insulator and a magnetic insulator. If you see this basically this magenta color is topological insulator, this green is magnetic insulator. And what you see is that this magnetism penetrates into the topological insulator up to 1 or 2 layers. So what we could see is experimentally, it's not just the exchange field that sort of couples the magnetic insulator to topological insulator, rather it is because magnetism penetrates, that is, there is a certain hybridization that makes the topological insulator magnetic. And now, because the surface states are magnetic, you can have exotic things that happen at the field scale of 20, 30 Tesla, now at very small fields. That is the advantage. And we have looked at some, so I would ask a very simple question here, that you always apply out of plane fields to realize quantum Hall or any exotic field. So what we did was you have topological insulators whose surface states are very nice, they are surface conducting. But what happens if you go to the bulk? Like you can sweep the gate voltage, you can go in the Fermi level. So what we saw was something really interesting. When we apply an in-plane magnetic field, we saw hysteretic magnetoresistance. I think the transitions aren't working properly, but if you focus on just this curve, then there is a certain hysteresis in the all measurements. Try to just get that one. Okay, it's saying the same thing. But if you try to look at just this hysteresis, that too in an in-plane magnetic field, this basically corresponds to very non-trivial spin textures that have been formed in topological insulator magnetic insulator interface. And if I have to show you a picture, it's something like this. You have a topological insulator, you have just put a magnetic insulator on top. Then there is a large spin-orbit coupling of topological insulator, which can actually change the properties of magnetic insulator as well. The first story I told you was that magnetism is going to penetrate into the topological insulator and give you exchange field effect. But the reverse can also happen, where the topological insulator can influence the properties of the magnet also. So, and this you can do by simply applying in-plane magnetic field, which are again very, very tiny in magnetic field. So you can tune the properties. That's the whole idea that I'm saying, by carefully growing materials one on top of each other, and MB is the way to go for this. And secondly, it's these material research that is important, because there are this, for instance, you want to realize something in quantum technology, and if I say, hey, I need 20 Tesla magnetic field, you're going to kill all superconductivity, end of the story, nothing remains. But when you engineer materials and properties in a very specific way, where things like this, fixed material platforms like this, where you substitute for external magnetic field, but you provide the same magnetic field, then these are the material platforms that are important for quantum technology. You have topology, you have extremely large magnetic field, but you're not applying any magnetic field. So that's the kind of research direction we are moving into. And similar kind of things we are also looking into in superconductor ferromagnet hybrids. I think I don't have, okay, so give me 3 minutes and I'll tell you a bit about what happens now if you have a superconductor and a ferromagnet coming together, okay? So first thing, if you might remember from your Michael Tinkham book reading that superconductor is upspin, downspin, and then connected opposite momenta and net momentum is 0 connected by a phonon. Whereas ferromagnets are spin aligned, so they are antagonistic in nature. But now if you put them together, you expect ferromagnet to kill all superconductivity. Right? That's very natural. But it doesn't happen like that because this was just the BCS formalism or Bardeen-Cooper-Schrieffer formalism that you will have triplet pairing. But it also turns out that you have that was singlet pairing, but you also can have triplet pairing in superconductivity, where superconductivity can survive ferromagnetic correlations. And we are looking into experiments where we try to pass Cooper pairs through ferromagnets, simple ferromagnets such as iron. Now, iron has just the spin. So if supercurrent passes through iron, then one of the quickest claims is it must be triplet paired superconductivity. So we also take help of platinum, which is a spin orbit coupling material, and we are trying to look at experiments where you'll have triplet correlations in the superconductor ferromagnet hybrids. So there is point number 1, which is hiding. I'll tell you a very interesting experiment. You take a superconductor. Okay. So what is the meaning of time reversal symmetry breaking? You change current from I plus to I minus, then B plus should go to B minus, right? But turns out that when you have nicely, so the first point here is I plus goes to I minus. So in superconductor ferromagnet hybrids, what we found was time reversal symmetry is preserved when I plus goes to I minus, B plus goes to B minus, but always take care of what is the direction of magnetic field that you're sweeping. So the fact that you take care of direction in which you sweep the magnetic field means it has some memory or hysteresis, and this is directly sort of hinting towards triplet pairing. Otherwise, you don't need any memory at all. I plus goes to I minus, B plus should simply go to B minus, but B plus will go to B minus only when you take care of direction of field sweep is a good hint about triplet pairing in superconductivity, and this is again thanks to proximity coupling where you pair superconductors with ferromagnetic hybrids. So I just want to leave it 2 messages that you can tune the material properties from in topological platforms by engineering the interfaces, number 1. And secondly, it's the same thing, but even in the context of superconductors, you can observe triplet pairing or unconventional superconductivity, again by carefully engineering these heterostructures and measuring the properties. These are 2 things, and its relevance is directly in quantum technologies. I wouldn't have said this if it was a purely physics science conference, but nowadays this is something I'm facing wherever I go. Everyone asks me, so what? This is a question, like you explain all the science and people ask, what's the application? What's your product? This is the kind of questions which people are asking, which also hints to us that we are moving towards this revolutionary phase where we are not looking at just scientific problems and enjoying the physics and having fun with physics and doing what we like, but we are also in that direction where we want to ask the question of its relevance. So what's it for? What's the product for? What's the technology for? And I think that's where we are moving towards, and that's where we are headed. At least that's what I see. And I think talking to you all would help me shape my future as well. Like I always ask, I would like to ask any of you on NQM or quantum tech is all great, but all of you had these research dreams before NQM. What happened to those? So right, I mean, this is really a question in my mind. I haven't got an answer. But fortunately, this field of topological insulators, superconductors, it is in the heart of where we are moving towards, and hopefully we'll see some nice physics out of our lab in future. Thanks for your.
Thank you, Elda. We have time for a couple of key questions.
Yeah.
Very nice. Thank you, ma'am, for a very nice talk. I want to a question regarding that where you talked about the magnetic field, high magnetic field in plane.
Yeah.
Suppose if I am applying very high magnetic field and out of plane.
Yeah.
Then the properties will change.
Sure.
So how it will behave like the spins and.
So are you there are two contexts. One is topological insulators and other is superconductors.
Superconductors.
Okay. So if you apply an out of plane magnetic field, you might have read about the Meissner effect, right?
Yes.
So
Yes.
there is a pair breaking potential at which superconductor state turns to normal. The advantage of so you can do this up to a point called critical field of any superconductor. That's the limit we have to operate all of this. Now, if I apply a certain in-plane magnetic field, that doesn't hinder anything. The critical fields are extremely large in the in-plane direction. So I can apply, I can have a magnetic insulator which is magnetized in the in-plane direction. That requires less than 1 millitesla of field, whereas to break the pairing potential in the out of plane direction, that requires about 7 to 8 Tesla field. So that's the reason why I would go with in plane, because it requires extremely small fields to see any effect, and it also survives superconductivity. Yeah.
Thank you, ma'am.
That's it.
We have one question from Shika.
Yeah, so that was a very nice talk,
Thanks.
very nice talk. What I wanted to ask, in addition to this exchange coupling, do you also have some strain in the
Sure.
waves?
Yeah, there is always this strain. So we can quantify this strain effects, and they are really very small compared to the effects that we see. That's number one. And strain effects in these systems, at least, they are not magnetic field dependent. And when we are talking about proximity coupling with a magnetic insulator, all measurements are sensitive to magnetic field. Strain is not as much.
So what kind of strains you are talking about?
So it's basically because of two things. One is we are doing MBE growth, and the lattice mismatch will be there between materials. So that will naturally bring in some strain. So that's the main component. And second thing is you can have some roughness, and that can give strains in the axis also.
Is it a quick question?
Yeah, it's a quick question.
Yeah.
Is there any effect of inversion symmetry breaking also playing in this?
In which one? So there is.
So when you
which-
mentioned that metal is.
Yeah. Yeah, there is. In fact, if you're talking about topological insulator and magnetic insulator interface,
Yeah.
and the spins getting a spin texture,
Yes.
it's because you have a large symmetry, large spin-orbit coupling and inversion symmetry breaking that gives rise to Zalosensky-Moria interaction,
Yeah,
and that gives rise to spin.
that's why the in-plane field is so much more.
Yeah.
Yeah.
Thank you. I'm sure there are many more interactions possible, which will continue over lunch. Please join me in thanking Dhavla once again.
I request the session chair to kindly give a message.
They were checking.
There you see that 245. Like, the speaker can see. Oh, yes, yes, He's not. He's showing this. He's my brother. He knows me from the day I was born. He was the first one to see me.
It looks like you don't have to take this plan yet, but we'll start it.
Maybe who is there in the dining? There is someone.
I'll find it.
If you give a call, then we will.
So good afternoon, everyone. Welcome back to the International Conference on Women in Quantum Science and Technologies. We will begin the first session after lunch. In this session, there will be two talks, and I would like to invite Professor Shugoto Ray to come and kindly chair this session.
Good afternoon, and I'm sincerely thankful to Professor Tanushree Shahada's Gupta and also Saqib for inviting me to be part of this event. And it's purely their affection why they have put me here as a chair, and I doubt I really have the sensibility to be a chair. But so let us begin the session. The first speaker of this session is Dr. Sukarna Sinha. She is a PhD in theoretical physics from University of Maryland in field of quantum field theory and general relativity. She has been associated with ISI Bangalore and previously with University of Mexico, RRI, as well as IUCA. I heard that she translates book. I never read it. I'm really sorry, but the book a physics book, Mahaparsher Kotha.
No, no, it's not translated. It's my.
It's your own, sorry, I'm sorry for that. A book without an equation or mathematics in that. And she will be speaking about this legend, her mother, Dr. Purnima Sinha.
Thank you so much. I'm very technology challenged, so I hope I get, instead of forwarding the slides, I might be going backwards, but so it's, I'm very, very grateful to the organizers and especially Sir Tanushree Sharada for inviting me to give a talk and in this very wonderful forum. And it's especially very, it's an emotional thing for me also because it's about my mother's life and work. And I was very moved to see all the speakers in the morning refer to her in various contexts in their inaugural speeches. So, so I'm going to basically talk about. So it's going to be a little personal with some personal anecdotes and basically tracing her life and also her connection with her PhD advisor, Professor Shatan Ghosh. And it's an honor to be here in a conference which is named after BOSEStat at 100 because he really was instrumental in shaping what my mother's career turned out to be. Okay. So let me first go through a quick timeline and then I'll get into a bit of detail on this. So she was born in Calcutta in 1927, so she would have been 97 now. And then in 1947, she did her BSc from Scottish Church College, Kolkata. And then 1950, she got her MSc in Calcutta University. And 51 to 55, that was, started her PhD. And see, 53, somehow I put 1956 as a marriage because that's what I got from one of the sources. But then I remember that it was 1953, the day Edmund Hillary conquered Everest, 29th May. So it's just that it was documented as 56 because it was sort of kept secret because it was an intercaste marriage in those times. So, even though she was married when she got her PhD thesis is titled Purnima Sengupta. Okay, so then she got 1956, those days they called it DPhil, first woman to be awarded a doctorate in physics from Calcutta University. I put down Calcutta University very carefully because probably it is in all of India, but since I don't and in the absence of a counter example, that's what I think it is. But since there is not adequate data, I'll just stick to that. Then she worked for a while for a year in Geological Survey of India. Then she spent a little time in the US, moved with her husband, who was a visiting professor, and worked in the biophysics lab at Stanford University for a year. Came back, worked at the Bose Institute, and like Professor Manna was referring to in the lecture this morning, for a long period. And she retired from there in the CSIR lab of Central Brass and Ceramic Research Institute. And she passed away in 2015. So I want to start out with her early childhood and her family and influences because I think it is very special. And I would say that as a woman physicist who was a pioneer, she is sort of an isolated data point in terms of how she had to struggle and overcome barriers because she had a very special family, a very supportive family. So she was the 8th and youngest child born to Naresh Chandra Sengupta and Vladimir Prabha Sengupta. Now my grandfather, Naresh Chandra, was a reputed constitutional lawyer and a scholar of jurisprudence and a very well-known, very progressive author who had written over 60 novels. And he was really, really very, very deeply committed
to the cause of women's education, and that was reflected in how he raised his daughters with a lot of freedom, really no limits to where they could go. So when she was growing up, she absolutely didn't feel that there was something that she couldn't do, science, engineering, whatever. And she had role models. She had role models who were way before her. And my eldest aunt, her eldest sister, Shushama, who was 24 years older than her, in 1903, she was the first woman to receive a master's degree in economics from Calcutta University. And then she started a school for girls, which was a big deal at that time. And then another sister, Tanima, 1913, who was 14 years older than her. And she was, I guess, a contemporary of Biba Chaudhuri. And so she was also the first woman to receive a master's degree with thesis in chemistry from Calcutta University. So they were, I mean, they were sisters who were already there. So she knew that this could be done, you know, not only in humanities as well as science. So it was a very special family. And I should put down, I mean, he was one of the biggest influences in her life, her father, and he shaped the way she thought and gave her the confidence to realize that she could do almost anything. And another very important thing is that in the, as she was growing up, and she was born in 1927, and not only was she not told that you cannot study this, you could, first of all, studying higher education itself was a big deal at that point, but doing science was even a bigger deal. Not only was she not told that you cannot do this because you're a woman, the other thing is that there was absolutely no pressure from the family for her to get married, you know, and I think that is a very big deal because just recently I was in a workshop where I met this very young, promising neuroscientist in her mid-30s, and she's done postdocs in some of the best places in her field, and she was getting constant phone calls from her family pressurizing her to get married. You know, this is 2024. So it was quite exceptional that at that point there were no such pressures. So she started her schooling in Lake School for Girls, which was a school established by her elder sister, which was also, she was also a big pioneer in the field of education and advancement of women. And it was a stage at which she started the school where parents were saying, we don't want to send our daughter to a school where she has to cross over the tram line. So, you know, it was that bad. And then she started her, so that also had a big influence on her. So she started her MSc as one of the first post-independence batches because it was in 1948 and that was just after independence. And she was the only woman in a class of 60, which is not surprising. I think it happens in the IIT still, and back then, of course, it was there. And that was the golden era of physics in Calcutta University because she was taught by stalwarts like S.N. Bose, Emil Shah, Inar Sen, Shishir Mitra. And what she did, she had an MSc, you had to choose a special paper. And her special paper was X-ray crystallography, taught by S.N. Bose. And that influenced her a lot, you know, like that. She found that extremely exciting and his teaching extremely you know, inspiring and stimulating. So she decided to join Professor S.N. Bose as a PhD research scholar. And the problem she was given was X-ray analysis, like some people also spoke about it in the morning, of clay minerals of India. And this was, strangely enough, funded by the Assam Oil Company, by an industry. And that was also very unusual. And not only that, because it was funded by an industry, her fellowship was at that time 300 rupees per month, where, like government scholarships were 75 rupees. I think my father was getting 75 rupees and she was getting 300 rupees. So, because it was industry. And it also shows that, at this point, to also contrast that SN Ghosh, of course, had absolutely no hesitation taking her on. He was, very keen on taking her on. So he actually went to he was good friends with her father as well. And he said, give me your daughter, I want her to build big instruments, So, so contrast this with Raman's attitude towards women, or even DM Ghosh when he took on Biba Chaudhary as a student, where he finally took her on as a student, but he was very reluctant and has a lot of hesitation. So SN Ghosh was way ahead of his times, definitely, in this aspect, and all through her association with him. At no point had she felt that she was discriminated against as a woman at any point of time. So it was very, very, he was genuinely a person who believed in equity, equality. Okay, so the other thing is that it was the labs, this was also a time for nation building in some sense. It was just post-independence. And the unwritten law in rule in the lab, Khoira laboratory, was that nobody orders instruments. In any case, it was very expensive, it took time, but that's not the idea. He wanted everybody to fabricate their own equipment. So, so everybody built their own instruments. So, RPM's idea of Make in India really was like implemented way before in time. So, so what she did is she needed an extra tube to do her experiments. So she built her own. And how she built from scratch. And what they did, there was a place near Wellington Square where they sold. This was also right post World War, right? This was 50s. So they had World War II surplus of various instruments. So she picked up scrap from there and at low cost and put it together in Science College workshop, and she built the stuff. Built her own instruments, took data with it, all of that. And then later her research results were published in Nature. Now, the interesting thing about it is that, and this is something I saw, and she talked about it later, that he was, though we know of SN Bose, this is the 100th anniversary of Bose statistics, which is, and he was a theoretical physicist, almost a mathematical physicist, but he set up all this experimental work, and he took a lot of interest in it, and he had a very good sense of it, looked at all the details of the instrumentation, data taking, everything, gave a lot of interesting inputs. So he was very much involved in it. And so that is something, and this is something I saw this is of course before I was born, so I don't know about this stuff firsthand. But later on in life, I saw like this supreme confidence in taking instruments apart. She was always repairing stuff, and she loved working with electricians, masons, all the workmen. Like she was just working shoulder to shoulder with them. She understood their language, liked working with her hands. And this is sort of completely in contrast with, as I said, there was a gender stereotype reversal in my house, because my father was even scared of holding a screwdriver. So, it was completely different. So that's how I grew up seeing, reverse stereotype roles. Okay, so regarding this instrument building, so this was a very impressive thing, and she got it to work and took data with it, and she got a lot of collaboration and cooperation from senior students in the lab who were also doing this stuff, workshop people, all of that together. So I have two interesting anecdotes in this respect regarding this building of instruments, and one is about S.N. Bose, where once she had gone to his house while she was a graduate student, and his daughter, and she hardly wore any jewelry, which was unusual at that time. So his daughter said, like, why are there no bangles on your hand? So before she could answer, he chipped in and he said, so let me say the sentence in Bengali and then I will translate. He said that, ও চুরি কেন করবে? ও তো রান্না করে না, ও বড় বড় যন্ত্র বানায়। So it's not that she's working in the kitchen. She builds big instruments, so she doesn't have to wear bangles. And the other story is about my father, because he had gone to the US for some work, and then one of his friends said, like, just in case you want to buy a present for your wife, where shall I take you? Which shop? Do you want to take you to a clothing shop, a jewelry shop? So he said, take me to a hardware store. So, and there he bought an electric drill for her, and she was very, very happy with that. So that sort of showed like a very, so this slide, of course, doesn't belong for this audience. I think I was giving a talk to IEEE women, so everybody knows what X-rays are about. So basically, like put your sample and reconstruct the structure from the diffraction pattern, right? So now the thing is that, again, we don't, mostly the Bose is known in the world as a theoretical physicist, but he had traveled to Paris right after his work here in 1924, and he worked in Maurice. He took I think, study leave from Dhaka University, and went there, and he worked in Maurice de Broglie's X-ray laboratory to learn experimental techniques of X-ray diffraction analysis, and later set up X-ray crystallography labs both in Dhaka and later in Calcutta. And I find that a remarkable feat, I mean, which theoretical physicist now is going to do something like that, and this is a part of Bose, I think, which is not, because he didn't have so many publications in this area, not very well known to the world. So let's also put it in some historical perspective in terms of dates. So Watson and Crick discovered the double helix structure of DNA using Rosalind Franklin's X-ray diffraction photograph in 1953, and that's just about the time Purnima Sinha was also working towards her PhD. Yeah. So X-ray crystallography was in a very nascent state. It was the exciting new thing to do, and S.N. Bose had picked it up and established it here, and he had a woman student working on it. All of that was very remarkable. Okay. How am I doing on time? I'm not looking at the.
So you still have roughly 20 minutes.
Okay. So this is a quote from an article in Leelapati's Daughters, which actually she wrote jointly with my sister. So this is how she describes the journey, which I've already talked about a little bit. Around the middle of 1951, I started working on my PhD with Professor S.N. Bose at the Khoira Laboratory in Kolkata. He advised me to carry out an investigation on the structure of clay from various parts of India. He suggested that I could use techniques of thermal and chemical analysis along with my X-ray scattering, and also suggested that I fabricate my own X-ray tube of the Coolidge kind so that the parts could be dismantled and put together at will. So as So Mr. Manna was also saying in the morning, now there are two aspects to be noticed here, that this was about indigenous clays, like this is also a very interesting thing that, you're working on something that is specific to India and you're finding out structure of that. And that is why the Assam Oil Company was also interested, because the chemical structure actually affects all about the oil drilling and how so that's why they were paying so much. And it lies at the, like Dr. Dashgupta was also saying in the morning, that he had a lot of input on Ashima Chatterjee's chemistry projects in the beginning. So really he had this was an interdisciplinary field where chemistry, geology and physics came together. And so there were a lot of cross-disciplinary angles to this also. And in fact, she had a lot of interaction with the chemistry group in Calcutta University, Ashima Chatterjee's group, because the chemistry and the physics of the structure sort of went together. And the whole idea of finding out more about Indian clays in particular seemed to be, like a very, also a slightly offbeat and an interesting project. And I think it also has something about, first of all, clay structure, as he said, like it's not that trivial because it's not purely crystal structure. It has also amorphous components, so it's not so trivial. And secondly, it is also like post-independence. So you really want to find out, more science that is rooted in your country. That might have been one of the angles as well. So here she also talks about that, that the more experienced research students used to initiate newer students in this mode of doing research, and Professor Bosch would routinely keep track of the problems we faced in the lab, as well as our progress. There was constructive cooperation between fellow students and people working in related departments, which is quite remarkable, and she didn't feel any hostility or animosity in any area, even collaborating with other senior students or other departments. So it was quite a remarkable atmosphere, and I think the tone was largely set by S.N. Bose in some sense, how he, if you have a leader who sets the tone like that, the entire group develops that culture, which is very remarkable. And you see that deviation from that culture 30 years hence, which is sad. So this is also a curious historical snippet about crystallography as such, and I just put a link as well, because these days in the internet you never know like what you find. So there has to be like, so for example, I have found articles on my mother saying that she had to build her own X-ray equipment because she couldn't get funding, or she had ordered and instruments didn't arrive and all that. So people just make up their own stuff and put it out there. So you have to be careful about what you see out there. So here is, strangely, I didn't know about that. The Braggs were very progressive in their attitude towards women in science. And out of 18 research students that they had, 11 were women. And Kathleen Lonsdale was a product of this lab, and Dorothy Hodgkin, of course, went on to win the Nobel Prize. Kathleen Lonsdale herself was the first woman fellow of the Royal Society, and she did a lot to advance the cause of women in science. Yeah. But the last line, strangely enough, today the International Union of Crystallography's online list of eminent crystallographers is more than 90% male. So I don't know what happened in between. So here is a thing that I just wanted to, not directly related, but I wanted to put it up, because this is a tin can made into a simple diffraction camera by Kathleen Lonsdale at the Royal Institution, and this is in the Science Museum group collection. And this is very reminiscent of picking up scrap and making stuff, look at that. And Jagadish Bose did a lot of this also. So, so this, I think this whole attitude has gone now. Of course, instruments have become, as we saw, like all the, whatever, the talks in the morning, you cannot, the precision has gone so high, you can't do this kind of stuff. But the spirit, I think, is very important. It was, a lot of that was there also with Raman and in Raman's time. And I found this rather interesting. Yeah. Okay. So now, so this is her, this is the first page of her thesis, which was submitted in November 1955. And as you say that it's Purnima Sengupta, because that was her maiden name. And here are some pictures from her thesis, X-ray diffraction patterns of Santal Pargana bentonite, Nimladi bentonite, various, clays and their structure and their diffraction patterns. The other technique she used was differential thermal analysis, and so she looked at it in these two aspects put together: X-ray diffraction, looking at the structure, and this differential thermal analysis as well. This DTA machine was also fabricated in Calcutta University lab. I think this was done before her time, but still it was like an in-house thing. This was done by some other students, and she used their equipment. So these are the techniques that she used. And this is a picture of the group. Now, this is, as I was telling Shubha this morning, that I had a personal copy of this, but I couldn't find it. So this is a screenshot that my sister took from the documentary she made on SN Bose. So here my mother is on one side, and this other woman, I think she dropped out. Her name is Leela. I don't know much beyond that, but this is sort of the entire group. The man standing next to, let's see if I can get this. No, I don't think so. What do I have to do to make this pointer to work? Red button. Where is the red button? Oh, okay, here. This one. He was my mother's senior, Jagdish Sharma. He also got his PhD from with SN Bose, and he was a lifelong friend, and he was the one who took her around to these scrap yards and sort of inducted her into this instrument making a lot. So, this is the picture. Then there is this iconic picture sandwiched between two statistics, Bose and Dirac. So Dirac visited in 1954, and so she was given the responsibility of showing him and his wife around Calcutta. So she interacted quite a bit with Dirac in that context. So this is in Shibpur Botanical Gardens. Not a very good picture, but it's very good. Okay. Yeah. So I thought I should also mention trailblazers who came before, because she was 27 born, and here was Biba Chaudhuri, and we were just discussing after lunch that though Biba Chaudhuri is now a well-known name, for the longest time we knew nothing about her. Nothing was known about it, and that says a lot about how women's in science are sort of treated, and how they're just like Shohini also showed, like everything is missing suddenly. So similarly, Biba Chaudhuri's name was not known until it suddenly came out. Like I guess just how long ago? Maybe not even a decade, right?
Yeah. 16, 17, 2000.
Yeah. So on the other hand, she'd been working since, she got her PhD in physics in 1949, and she was 14 years my mother's senior, and of course she got a PhD much before before Purnima Sinha, but she finally got her PhD from Birmingham. Yeah, so she moved, no, yeah, Manchester she moved to. So, uh, but her work was very, very important, she almost found the pile. She did cosmic ray research in very difficult trying circumstances, and nobody knew about her. So this certainly, is worth mentioning. And Ashima Chatterjee she was of course again my mother's senior, and she got a PhD or a DSc rather in 1944, which was long before. But she I think was the first woman to receive a PhD in all of India in science. Yeah, but Purnima Sinha had a lot of interaction with her lab and her chemistry students, so things were few and far in between. Yeah. So later work, just keep telling me the time, otherwise, I don't keep.
Yeah, 5 or 7 minutes.
5 or 7, it's okay. All right. So now the thing is that now naturally there are interruptions in careers. So right after her PhD, she started working in the Geological Survey of India because her work was also related to geology. But as happens, that time her husband moved to the US for visiting positions for 3 years. So she moved with him, and first without a job. Later on, she worked in the biophysics group at Stanford related to the origin of life, connected with the idea originally proposed by Bernal, saying that clay surfaces may have been the substrate for the original pre-biogenic polymers. And now this stuff is still speculative. So, and I don't think like much progress has been made in this field. So there were no publications in this, but this remained lifelong interest. So then she joined Central work for Bose Institute. In Bose Institute, she continued her origin of life work, and then she joined CGCRI, Central Glass and Ceramic Research Institute. She continued work on clay mineral and X-ray analysis with applications to ceramic color. And then she worked on a very interesting project in collaborating with traditional potters of Bakura on ceramic glaze, giving them the scientific know-how and learning from them as to how they get things to work. That was an interesting project. Now, I could stop here because this is all science, but Purnima Sinha was not all science. So, and the non-science part or other interests, she was a very multifaceted person, and there were many dimensions to her. And that, if I'm talking about her work and life, that should not go unmentioned. So as somebody mentioned before, that she learned tabla from Pandit Gyanaprakash Ghosh, where tabla was exclusively a male domain. She also learned vocal music. Not only that, she worked in musicology. She wrote an entire book called The Approach to the Study of Indian Music, based on a series of lectures she gave in Chicago University on Indian music. Much later in life, she traveled to Andamans with her husband and heard these Aboriginal tribal songs by the Jarawa and compared it with the Vedic chants. And it was not just a loose comparison; it was a very thorough musicological analysis. So the music is one aspect, and then there's art. She again, clay remained part of her life all through. And all this stuff, so she built, in our Shantiniketan house, she built a kiln and worked with, this is a mural she has done, which is still there in Shantiniketan Vice Chancellor's house. This is about 12 feet long, done in cement. And that one out there is a collaboration with potters, because the whole thing was conceptualized by her, but each piece was thrown on a potter's wheel and then glazed and fired. So, and this is just a part of it. She also had a solo art exhibition of her own. Then the other thing is that this is also something that S.N. Bose was deeply committed to, propagating science in the mother tongue. So she did a lot of science writing in Bengali. she wrote a very wonderful biography of Chopin Ghosh. Then she translated Schrodinger's Mind and Matter into Bengali. So that is also a very remarkable piece of work. And post-retirement, they lived in Shantiniketan and they had an informal school with the local tribal children. That was also one of her commitments. And very late in life, when she was severely affected by this macular degeneration, where she could just read like one word at a time with a lens, her deep interest in biology continued beyond her biophysics research days. And her last piece of work at 80 plus was an excellent Bengali translation of this book, Unraveling DNA, which unfortunately for certain reasons could not be published. So one other thing I missed telling you is that in her thesis, there was a picture of her X-ray equipment and her standing next to it. And then some random person came and said, you know, I'm going to do an exhibition. Can you lend me this picture? I'm going to return it. So she just ripped it off her thesis and gave it to him, and it was never returned. So that picture is, that piece of history is gone forever. So we don't have a picture of her equipment. So that it's just got a title in a blank page in her thesis. So that's a very sad thing. We still feel very sad about. Okay. So this is a biography of written by Rajendra Singh and Shubhakar Shah. And I think she wrote Dr. Chandima Shah wrote the forward for it. So this is, so thank you very much for the meeting.
So I think any comment, any observation there? Please, I mean. A discussion. Yep.
I'm just curious that you spoke about SN Bose's view, right? I mean, he was very open to having women students.
Yes.
So, I mean, I'm just curious, I mean, what about his family? Like, did he have like children who were, or?
That is a very interesting question, actually. And like many people who actually had very liberal views on women, I don't think his daughters, youngest daughter, I don't know so much about, but the older daughters definitely, I don't think they went into education a lot. It was also a product of the times. It's true.
Yeah,
Yes.
the personal incident.
Yeah, definitely.
Just a scientific curiosity, I may be wrong, please correct me if I'm wrong. I've heard about the setting up of the diffraction experiment where Bose just took a book and sheets of the paper. Like
That is
so
JC Bose.
So that was not.
That is JC Bose, and that was a polarizer. That was a
So that was.
polarizer. That was from a railway Bradshaw, you know,
Right,
like
right.
it was. These days, you probably your generation wouldn't have seen that anywhere. You know, you're all on the internet. These were the railway timetables, which were about this size, and you know, he just layered it. And I don't know. I think there is a JC Bose museum. I think that might be there also.
Yeah,
Yeah, so it should be there.
Any further questions or comments? Yes.
I'm just curious, I mean, of course, everywhere it's written that, you know, from this World War II, there were some of this remains thing, and that were collected from there.
Yeah.
So, I then thought of even that possibility, was it?
See, I think they were very resourceful. This Jagadish Sharma, you know, they were trying to cut costs always, you know, like, and looking around for how you could get things. It was not easy to, and these things probably came from Britain, right? So it was not easy to order anything from there. It will come by ship. It will take a long time. So this was out there, you know. So they were looking for. They had to build a transformer, a step-up transformer up to 30,000 volts, you know. So they got pieces out of that. High vacuum pump, they got pieces out of that, modified that. So I guess, like, you know, they were just resourceful. That How
In
much
this
stuff?
context, I just wanted to ask, I think it was raised after this talk, that India never had proper workshop or proper engineering backup. So how was the thing in Calcutta University? I don't think they had those.
See, things were still very primitive then. Still was there. Yeah, so now the kind of refined experiments or the high precision that you need, I think that needs a different ballgame altogether. But at that time, this was sort of on par. I think it was adequate, and what my mother says that the workshop workers were very skilled, and there was just this spirit of we're going to build it all ourselves. Just here now you think that probably it's not possible, so how are we going to do it? Then there's no and also it's like a necessity being the mother of invention. You don't have a choice, so you make it. So that was sort of the spirit. But I agree that the precisions were low, but the workshop was very active at that point. Whatever they were working hand in hand within the precision and ability of the. I mean, I was not there. I mean, both of us. I'm also no theoretical physicist, so I don't know any of this stuff. This is all that I've heard from my mother. So I think they felt that the workshop workers were very participative, very cooperative, and like they were willing to work late into the night. There was that spirit of going, and it was adequate at that time, for their accuracy. So I think now what you say is certainly you need greater expertise, greater technological expertise.
So I was reading through the joint piece written by your mother and your sister.
Yeah.
And where it's, your mother's comment that SN wanted to have this culture of building of things.
Yes.
Which has been, as you mentioned,
Right,
has been
right.
at a drop.
Right.
And I definitely say as an experimentalist myself that this culture has never developed. We have workshops which are not for developing things. If for everything we look for engineers from outside, our workshop probably does a little bit of repairing job, nothing other than no development.
But Ram did a lot of that, and even RRI for the longest time had a lot of, RRI had this, I forget his name, Lakshmi Narayan, I think. He made this, noise isolation thing from a tire, and it worked extremely well. So I think Raman had that spirit. Of course, Raman Research Institute for I think 2 whole years didn't have electricity. So all the experiments, optics experiments were done with sunlight. So I think from then onwards, things just went south.
Your mother submitted to Calcutta University.
Yes.
Thesis. So they have now scanned a lot of theses even back quite some time. Do you know if hers have been?
I don't know. I tried to find out. I want to find out whether that picture I can recover that. But I have not been able to. I don't know whom to contact.
No, in internet it's available. All the theses they are scanned.
Is
So,
it?
yeah,
Okay.
I will try to find out.
Okay, that would be great. Because we feel very sad as a family at doing that. Yeah.
Yeah. But those yes.
Just a curiosity, how was her interaction with you? You are a physicist,
Yeah.
your sister is a physicist.
My interaction was our interaction with both our sisters. It was very good. Though that I had a very non-experimental bent of mine, so I just couldn't. I mean, that part of it I couldn't appreciate. But she was always very interested in my work. But she was always, interested in learning the latest stuff. So. To her dying day, she was always interested in like learning new stuff, and so we had a very very good interaction, both sisters, in terms of just that we didn't choose experimental work. That's
I think we have to move on to the next talk and then. So we move on to the next talk, and this will be delivered by Mrs. Sumati Rao. She's a very well-known theoretical quantum matter physicist, but she was trained as a high-energy physicist in Stony Brook University during her PhD days. So I think I just invite her to kindly share her experience of life.
Let me begin by thanking Tanushree and the other organizers for inviting me for this workshop over here. And Tanushree asked me to talk about gender diversity. So I chose the topic to be the history of the working group of women in physics in India. As we just heard from the last talk, we've always had a few individual unsung women in physics in India. But there's been, what I want to talk about more is about the recognition that numbers were skewed and that there were discriminatory practices and so on. So I'm talking about a later time in life when people started, there were very few women in physics and they started realizing that the numbers are skewed against them. And the thing is that for a long time, this was expected to be natural, not only in India, but also the world over, that curiosity about science and physics in particular is only for men. So what I'm going to talk about essentially is the history of what some of the people here do very well about, the working group of women in physics in India. And also, after that, discuss slightly what is the status of the women in physics in India in current years, and going forward, what we can do to improve the situation. So I came into this in 1999, when in the International Union of Pure and Applied Physics, which is a global group. They decided to start a working group on women in physics, and this was formed by resolution in 1999 under the leadership of Judy Franz, who was from the American Physical Society. And essentially, she knew Nandini Trivedi. She wanted somebody from India, so she first contacted Nandini Trivedi, who's a condensed matter physicist. But Nandini Trivedi was just leaving for the US at that time, so she suggested my name. And then that's how I was in the working group from 2000 to 2008. And the mandate of the group initially was just to plan a single international conference on women in physics. And the idea was that you want to study why there is a underrepresentation of women world over and what you can do to help that. And so we were part of that planning group. And then the first international group on women in physics was planned. We decided the speakers, the topics, the modalities. We even got funds to have this conference. And since it was the first ever conference, it was held the world. It was the money. We found it easy to get the money, and it was held in Paris in 2002. In the course of this, I was asked for an informal survey in 1999 of 30 women physicists in India. And this was, they gave me a questionnaire to send around. And I sent it around basically to people I knew, who sent it to people they knew, and so on. And what we found at that time, in 1999, was that the general perception of the women physicists in India was that there was no bias against physics as a subject in India. And almost no one in that entire group, I think 1 out of the 30 said that there's been discrimination. Everybody else said that they had problems, but it's their own fault. So nobody suggested discrimination at all. So for all of us, I would say that the first international conference of women in physics in 2002 in Paris was an eye-opener. The participants included Rohini Godbole as the Asian success story. She was also part of the 30, and 4 others, including myself, Nilima Gupte from IIT, Jyoti Ganchandani from BARC, and Sunita Nair, a young postdoc at that time. And during the conference, there was a very good one by Nancy Hopkins, who was a molecular biologist who just around that time had documented discrimination in MIT. She had done things including measure lab spaces and shown how systematically all the women had less. And so after that, during the discussion, we realized the commonality of problems and gender discrimination faced by women in 65 countries. This ranged from US and the Western world to individual scientists from various countries in Africa. And it was amazing to see that everybody had very similar stories to say. After that, the IUPAC Women in Physics Conference has been held every 3 years, because the first one we got so much response that many countries came forward saying that they would hold it every 3 years. They managed to get the funding and so on. And everything had been done by the women themselves, because until then, most of the women were not even in a position to gather funds. But it happened. And the mandate was to review situation for women in physics and suggest ways to improve. I would say for us in India, the main impact of the first 2 or 3 international conferences on women in physics was the recognition of the problem, that there is discrimination. So once we came back from that conference, when we started networking a little more, women started writing articles, giving talks, highlighting the problem. In the first, after the first conference when we came back, we wanted to write a report on it, where we also wanted to mention the words sexual discrimination, and that the editors, I think I don't remember, Physics News or something like that, suggested we don't do it because it will offend people. So we have to, so even to just mention it was considered a taboo in as late as 2001 or 2002. So what I would say is IUPAC, this WIP really seeded discussions among working women physicists in India. Then people started holding special sessions on women in physics and conferences we attended. Nilima Gupta in StatFizz 2004 held a side this thing on women in physics. Pratibha Jolly in 2005. And one of the most important things that came up was this INSA report on science career for Indian women. This was a committee which included Bimla Bhuti and Rohini Godbole and from physics, and then some other scientists as well. And this INSA report came in 2004. Before that, the only data that we had, because when we went for these conferences, they wanted us to present data, was something which was collected by Nandini Trivedi in her individual capacity, because her parents are IAS officers and she could manage to get some data which was not available before that. So this particular INSA report was an important document which included data on women in science for the first time. They didn't divide it between physics, chemistry, biology, but at least we had data on women in science. It highlighted the fact that in India, differences were not at the school level. In fact, girls routinely outperformed boys in school board exams in science, even at certainly 25 years ago. So the problem in India was never to attract girls to science, but to retain girls in science as they moved up the standard leaky pipeline story. So this was something we could report on the second IUPAC conference in Brazil. But we managed between ourselves to collect some data on women in physics, but it was sketchy. We did try at that time to start some kind of working group in women in physics, but it was not successful, partly because we did not have this idea of IPI, to which all women could belong. And things like the Academy, Indian Academy and INSA and all had maybe Rohini Godbole and nobody else as far as we knew from physics. So it was not really possible to form this kind of a thing. By the time the third IUPAC Women in Physics was done in 2008 in Korea, our individual networking via email and so on had improved. And there we already have slightly more representation from India. Pratibha was a plenary speaker. 3 of us presented at parallel sessions. And we even had people like Nutan Chandra and all who were participants from teaching colleges. And by then we had many successes to report. The Indian Academy of Sciences also formed the Women of Science panel in 2005. And it brought out this book which Suganya also mentioned, Leelavati's Daughters, which were 100 essays by working Indian women scientists, edited by Rohini Godbole and Ram Ramaswamy. It highlighted for, I think, the first time that normal working scientists could be women. I mean, it doesn't have to be Marie Curie, but otherwise the only name any person could mention if you talk of women scientists would have been Marie Curie. And this was the idea that you could have this as effective role models for women. And in fact, this book has been followed by a shorter version, The Girl's Guide to a Life in Science in 2012, answering the question of why choose a life in science. I won't go much over the next few. I was working the Women in Physics group leader till 2008. So I used to attend those conferences, after which I haven't. Then it was Shobana Narasimhan who was then the country leader. And later it was followed by Prajwal Shastri. And it was, various conferences were held in South Africa and in Waterloo in Canada, which Rohini also mentioned. And then in, I think, England and most recently in Australia. By then, in around 2017, Prajwal Shastri, with a lot of hard work, set up the Gender and Physics Working Group of the Indian Physics Association. By then, Vandana was the president or secretary of the group. So all of these things worked out and it finally came to exist. And as you can see, here is Tanushri, here is Suchetna, why? Sorry, I know you just suddenly get the name. Prajwal. And this I forget. Reshmi and Shubha.
And Vandana.
Vandana, of course, yeah. I already mentioned her. Yeah. This is this led to the first Gender in Physics conference in Hyderabad, Present for Progress, in 2019, under the leadership of Prajwal Shastri, Bindu Bamba, who's not here, and Sobha Chania. These two were from Hyderabad University. And ultimately, I would say all of this culminated in the International Conference on Women in Physics in July 2023, which was finally held in India. After 20 in Australia, it was finally held in India. It was held in an online mode, thanks to COVID also intervening. And also, I think financially, it was easier to hold it in an online mode. And this was actually mainly possible due to the hard work of Vandana here, who all of you know, and Shobhati. They really put in a lot of work for this. So with this, I come to the end of the history. So I thought I'd just basically say what are the things which have happened in India because over all these years because of this. The first changes that were done by governmental initiatives were mainly family-based initiatives. Because the INSA report also seemed to first show that most of the people are held back at the postdoc and early faculty stages because of family commitments. So it was mainly focused on the idea that it's because of family responsibility and children that women in science lag behind. Of course, this is true for all working professions. And for women in any profession, this is true. And this did lead to some kind of governmental policies to provide a more level playing field for women in science. It has led to something called career break fellowship for women in science to help them get back to work after taking a break for having children and so on. And these initiatives have worked because about 223 such fellowships have been awarded I don't know, this is old data, I'm sure many more have been awarded till now. India that way has generous childcare leave as compared to most countries for all government employees, not just for scientists. There have been policies proposed, but I don't think they've been implemented for flexible work hours for women. The PhD has also proposed a mobility scheme to help women scientists adjust to body problem. I'll come back to this later. But why only for women? I mean, these should be for both. But none of these have been implemented. And policies are essentially focused on family problems faced by women. And the fact that many people have utilized means that it has helped. So there's been a definite increase in the number of women in science and faculty positions, in the number of women getting projects, and generally in the number of women who are visible now as compared to 25 years ago. Regarding mentoring issues, a global survey of physicists showed that 81% of female physicists reported having female physics teacher. So that way, publication of Leelavati's daughters was definitely a step in the right direction. There's also been the Science Communication Wing of DST has produced video series called Scientifically Yours, which is also again a role model kind of a program. And gender in science is now taken seriously at higher levels. This would not have been true 25 years ago when we started. People didn't think it was an issue. They said anybody who's good enough would get in anyway. So INSA organized a workshop on women in science. This is a little earlier. Astronomical Society of India has had this. And more recently, there have been workshops particularly catering to women scientists to sensitize them to the problem and prepare them for leadership. So just to give a comparison, in 2007, the estimated number of women in physics at the PhD level was 20%, faculty level was 10%. That time we only made a survey of IITs and some major universities. It was less than 5% in elite institutes. There was not a single Bhatnagar award for a woman physicist. There was almost zero again. No one in policy making bodies, funding committees, academics. There was, I mean, Rohini was there, but it's like in practical terms, that's 1%. Right? Yeah. Yeah, for everything they would just say, oh, we are Rohini. But in 2021, it shows that 31% of women PhD students, 29% for postdocs, 14% for faculty. It's not gone up much for faculty. And in elite institutions, it's still around 10%. Percentage of women in prestigious academics went up to 6% from 3%. But this has gone up. Women directors, VCs, members of governing council, 16% from practically zero. This has also gone up to women getting IPA award, CV Raman lectureship, etc. 20% from again practically zero. So these two numbers have gone up. I think thanks to a lot of the policies that and people like Vandana and all pushing these people to do these things. It's culminated, of course, in 2019 with Rohini getting the Padma Shri and Aditi getting the Bhatnagar Award. So this is, now we can no longer say that there are no Bhatnagar Awards. There were also some other kind of very nice initiatives which were taken. There was an all-women issue of Physics News edited by Prajwal Shastri, Bindu Bamba and Vandana Nanal. This was in 2017, March 2017. There was an all-women issue of Current Science with Nilima Gupta and Sulabha Kulkarni. All-women issue of Resonance, again edited by Prajwal and Suneshna. In March 2019, again another issue of Resonance with all women authors edited by Ritisha and Suneshna Sinha. But with all these success stories, does that mean that we have gender equity and the struggle is over? Of course, it's no surprise to most of you that ground reality for most women tells still a different story. The gender gap continues to exist and there are persistent problems. Regarding workplace discrimination, there have been analysis. I think there's analysis from Subramaniam in 2014, which shows that you have to, I don't know how much rank holders need, but in any sense, women have to consistently do better than men to be considered equivalent. These were equivalent people, but of them, the women were mostly a higher percentage and low ranks for women 9%, whereas this was the other way around. And data collected by our questionnaires for 56 women scientists and 61 men scientists, matched on basis of age, universities, and national labs, showed that there was no significant correlation between gender and productivity, but there is correlation between gender and position. And women get as you might expect, get promoted significantly later than men. And as for anecdotal evidence, all of you know this. There are women who are still being told that there's a vacancy, that's why she's being selected. There, a woman going for work-related travel is told that her husband is there, that's why she's going there. They're told that they should concentrate on their family. These have become less now. These were very much so when we were a little younger, that they would be told nicely. I mean, people well-wishers will tell you these things. Women with scientists with children are often asked how they manage. And the stereotype of women being solely this needs to change. The other important point is that gender-based harassment issues are often underplayed, and women are told to take things lightly. This has changed in recent times, but even now we know just a few years ago, a counter complaint was filed against a woman who a victim of sexual harassment. This isn't something I need to say here. So sexually harassed women are often told to leave and go home. So one really important thing is that we actually have to realize that discrimination is not something which is practiced by evil intentioned or bad people. Not sexual harassment, but other kinds of discrimination is basically unconscious. And as Shravani was also saying, we all practice discrimination at various levels. And we can only change when it is brought to our notice. And in India, the changes that have started and need to be continued we have to continue to collect statistics and use them to show that discrimination is real. We need website for more networking among women scientists to summarize initiatives, serve as data service for women's people, exchange of information, and as she said, stop being invisible. All of these things have started, role model programs, awards, publicizing of pioneering women scientists, but they all need to continue further. Initiatives which are like all women issues of science magazine, they need to be followed up by, in a regular issue, also enough women being asked to contribute. It can't be only for all women issues. The standard things like freshers, flexible time and all need to be done, but they should not be used against the women. And you need support groups and mentors to counter discrimination and discouragement, particularly in the early part of the career. There have been many special programs which have started. I want to also highlight all the positives. Vigyan Vidushi program in TIFR has now been running for many years, which is a 3-week program for first year MSc or fourth year, 5 years MSc students to kind of give them an idea of what research is like and to give them role models. These very recently, 2 years ago, we started a summer school for women in physics at ICTS. I think the first All India one was held this year. It's a 2-week program for second year bachelor or BSLS students. And this was mainly spearheaded by Sukanya's sister Supurna and her husband Sat. And there are people who say that special programs for women should not be done because that is perpetuating the stereotype that women are not good enough. But I would say that these programs are needed because India is a very diverse country and not all the women are, there are women, of course, from maybe metro cities who are confident enough and don't need these special programs. But certainly there are women who benefit from these special programs as well. So we should continue them. But much more needs to be done. This is something I want to bring up because I think there may be policy making, if at all this can be done by policy making people. I think I have a suggestion for most women scientists are married to other scientists. This is something we have faced. This is something Prashant should know about. This is something that everyone here has faced for many years. And what we really find it unfair is that even now, young women are in two different institutes in the country. There are people in IIT Delhi and IIT Hyderabad. Somebody's in BHU, somebody's in somewhere else. And many times they're equivalent institutes, but they're not able to come to the same institute. So I would suggest that there should be some scheme by which you allow institutes, IITs, universities to employ spouses without using up an extra position. Maybe give them like they had supernumerary seats, give them a supernumerary position. So that the number of positions automatically increases if a spouse is employed. Because when I talk to places, they say that we can't employ the other person because we want a person in that particular field. Right? So that's the kind of excuse which is given not to employ a spouse. Many times, I think it's an excuse given. Earlier, they really didn't want it because they used to say that somebody will get 2 votes. I don't see how it means 2 votes, but those are the kinds of statements made. So this, if somebody can take it up and at a higher level and make sure that, because I think people will work much better if spouses are in the same institute. Particularly those people with children. So other than that, okay, what are the things that I would
Ten more minutes, 10 more minutes.
So I'll finish. The questions that need to be answered, we need to have constant monitoring of number of women at different levels, PhD students, postdocs, faculty, senior faculty, and see how they change with time and see how they change with changing policies. I mean, because you want to monitor the policies also and tweak them so as to improve it. And these kinds of questions still need to be answered. Even though the numbers in India have increased, the fraction at elite institutes at higher levels of decision making and in prestigious awards, the numbers have remained very small. So what can we do to change this? And these are also important things that how are current policies such as career breaks for women, etc., seen within the scientific community? Do people resent it? Is it seen as right or wrong? It is needed, but I think it should also be evaluated as how it is seen positively or negatively for women. Are they leading to gender equity or contributing to a backlash? And there is another question that has come up, which we are seeing when we try to take women for these special programs for women alone. How do we handle and account for regional differences within India? Should we have a affirmative action that in some places the women are doing better? And when we have special programs for women, do we exclude people from IITs and IISers who are already one step ahead of their the women in smaller towns and all who don't have the same opportunities? So various questions need to be answered because India is, as we said, not a uniform country. How do you differentiate between women from small towns and rural India and those from urban India? And so what is the need of the hour? We need gender sensitization programs for both men and women. We have to make sure that committees involved in hiring, promotions, giving awards are fair and non-discriminatory. It doesn't improve only to have women on there, because both women and men are probably, in some sense, have some inbuilt biases. This is very hard, yeah, right? Because unconscious biases are created from babyhood. So you need to have special workshops and trainings. First, help us first get aware and get rid of them. Because now, so these modules can teach us about gender stereotypes and how to avoid them. They can teach us how to conduct interviews for students, faculty, oral exams without being perceived as aggressive. It can teach us not to ignore voices and ways of speaking which may sound diffident or less assertive. But the point is, and it can also teach us to prevent sexual harassment and gender-based harassment. And we need to differentiate between the two. I mean, I assume there's probably no woman who has not experienced some kind of gender-based harassment. But not every gender-based harassment is equivalent to sexual harassment, and there should be ways of both of them need to be redressed, but perhaps differently. You should not confuse one for the other. The thing is, this is what I want to finally focus on, that many institutes have started lectures and workshops on this, but these happen only on Women's Day or on some special day. And generally, it's not everybody comes for it. It's not, you can't force people to come for these things. How do you make it compulsory for everyone? I don't know. Faculty, students, administrators, casual workers, etc. Everywhere, including ICTS, has these programs, but they are, and ICTS is one of the better places where people do try to come. But none of these things can work unless it is really made in some sense mandatory. In particular, people working at funding agencies and hiring, promotion and award committees also need to go through this. And this is something that you all already know. It's an international enterprise, and much of the progress in science has come because of people have questions that been asked and answered by people all over the world. So, and diversity implies that we include groups which have not been included, whether it's women or other marginalized groups. And India, it's basically class and caste, which are the more important groups. So you expect them to ask new questions, fresh ideas. And you need to build a scientifically literate society, because many global issues like education, health, environment need everyone to participate. And without that, it can't remain the bastion of the village. So to summarize, I've essentially started with a brief history of how the Women in Science program in India evolved. And I've also said that clearly much more needs to be done to achieve gender equity. And the need of the hour is gender sensitization programs for all. How we will enforce it, I don't know, but that is something which is related. Thanks for coming.
The comments and discussions, yes, please.
Can I make a couple of comments? I think you given very, I mean, of course, the talk was very comprehensive and nice. But just two things I would like to add. One of the things you mentioned about changes in the IPA. I think it is in the IPA.
Yeah.
It has also been possible because there were, in the last few years, we had Tanushri and Shubhaviti as a vice president in the IPA. So this has also helped in getting the decisions executed. The second comment I have is about this best practice training, which have to be done for all. I think that is absolutely essential, and perhaps it's also should be made part of something like research methodology or courses which are given by the UGC. And this training is absolutely essential at an all administrative level. Yeah. Because the people who take decisions, the deans and all that pick it up, that's a big part.
Yeah. So probably yes, for the students, you can make it at the research methodology level, which is what is going to be done in ICT.
Very nice introduction and very nice history. So I had two questions. One thing is we are doing one survey that Vandana also knows through IPA, and I think most of the people here would have received that survey. One thing we are seeing in that survey is about 25% women who are taking that survey do not know about the existence of ICC, Internal Complaints Committee, and which is quite sad.
Yeah.
So that was the one thing that we have to really make sure that the message goes through. And the other thing, I think, as you say, key biases, they may be decreasing, but at each level we see still there are gender biasing. And I think one of the ways to get rid of it is maybe more role models or more leaders like vice chancellors, directors as women, as we are seeing here. Tanushri is here, Professor Shubhra is here. And I think that is also another thing that should be conveyed to policymakers. That
And no, I do see what I'm saying is yes, we did it, and it has been improving because it was probably practically zero when we were younger, right? I don't remember seeing a single vice chancellor over there.
I just wanted to share an experience in terms of this
like I said, like when women have children and there were no creche facilities. When I was a postdoc in Ayuka, I came with a 4-month-old baby. And naturally, though the campus was very close and everything, it's very difficult. So we went to and there were a bunch of us having young children. So we went to the administrative officer and he pulled out a rule book saying that you have to have 30 women working in a whatever, it's a factory rule book. Only then you're allowed a creche. So I said, like, are women the only people only gender having children? Men don't have children. He said, like, what about the 100 men working here? So we had no answer to that, but he pulled out a rule book. He was also an ex-army man, so But the contrast was, then Jayant Narlikar was the director. And when we went to him, he, brushed aside all these rules. Next day, a place was assigned, all facilities was given. So, if the culture is set from the top, things can happen. Just like what I was talking about, SN Bose's thing, that if, at the top level, you set that culture, the rest of it follows, right? So I think those kind of people, so one can always cite rules and, difficulties and all that, but in principle, they can be surmounted. Thank you.
There's a question here.
Yeah, I just, you mentioned about this two-body problem and many of us have faced it. So if a additional position is created, very often there is a tendency to give the soft position to the woman. Very often, in many cases, the husband has a kind of a secured, regular kind of thing and a soft position. So the additional position created, there will be a tendency to give it to the woman and saying this is a kind of a quota position. I don't know. I mean, the society actually reacts to it in a very, very strange way. So I don't know. I can tell you that
it shouldn't be a soft position. It should be a regular position with all the necessities. Because I think there may be some cases where one person is better known than the other. But in 90% of the cases that I'm saying, both of them are equally good. They're getting in two different IITs or two different ISOs. And each ISO thinks, of course, they're better than the other, but that's what is one perception, right? So
yeah, but I mean,
I understand what you're saying, but I think that it has to be done some way.
Thank you for showing, there's been a lot of progress. So one thing we've noticed is that when you get more and more success in these kinds of initiatives, you actually, of course, get more pushback and backlash. For example, the main thing now we are hearing, and in fact, it has stopped many programs in Canada, is because there's been complaints that this is discrimination against men.
Yes.
So has this happened here, and what are your thoughts on how to deal with that?
Right now, it has not happened yet in India that at least we haven't heard that there's a backlash as yet.
People are discussing. People are discussing. May not be at the policy level, but people are discussing.
At the district level, because so far what I have seen is that the younger people are better than the senior people. I mean, so things are only, I would say that the slope is positive. Once the young people start being the other way around, I would say that's right.
Yeah, there's a question. Please.
So I think I just one thing I want to make a comment, as Professor Shukarna Sinha said, and also Professor Shikha Verma said, that the example set by people in a leadership position, particularly the ICC, at SNBO, since I am a member of the ICC of SNB and CBS, every year routinely they organize a program. This is the ICC members come and there is a workshop that is discussed with all students. So this is exactly done by SNBO. So I think that can be very well done by other institutions. The other thing is about the gender training. So I think in UGC, about the daycare thing, the UGC now has a mandate that you have to have a daycare center and all that. But you are talking about compulsory training, like, in universities, faculty have to do this refresher course and orientation course, and that can be easily implemented, that all has to go to, so that's the comment I had.
I agree. In many good places, these things about ICC on a yearly basis, it is once a year they have it, or once or twice a year. It has to be regular, in the sense it has to be monitored also through the year.
Yeah, I just wanted to point out, and I think Shubhrati will be say more details. You mentioned that the Shanti Sarup Bhatnagar award, you mentioned somebody's name and Aditi, yeah, and Rohini Godbole got the Padma Shri. But when did Archana Sharma get Shanti Sarup Bhatnagar award? Long back, yeah.
Not in physics.
Not in physics, but from a scientist, not physics.
Yeah, I was okay.
Yeah, but as a scientist, she got, and she also got Padma Bhushan, and both husband and wife were in the same department and they were complementing each other. Calcutta University Botany Department. So that is one example.
I see. I see.
Rarest of the rare.
Hello, ma'am. I got it. I just want to make one note that just want to have some suggestions like some of my fellow male colleagues especially mention like inspired faculty for the inspired faculty that age relaxation for a women candidate like 5 years age relaxation and they are talking that women are getting more advantages and there is another postdoctoral fellowship for especially for wives that is wives. So how to reply to them? Actually, I don't get any
Yeah,
answer.
this is exactly what she was asking. There's a backlash. The thing is that, I mean, presumably they will also have children one day, they will also, right? That's the only thing you can say, that, I mean, until they have it, they will not probably realize the problems that kids have. What do you?
Can I just add? Because even for Vigyan Vidushi or the summer school, which are any woman focused programs, you get that. But when you see that you are seeing an apparent advantage, it is because there has been actually a dearth of it. There is something which they are trying to climb out of the other situations and they have a lot other disadvantages which are not visible to you. That is why that is given. I don't think it should be interpreted as an advantage because it is just a helping hand to make it smooth, to make it.
But most of the guys will say that, oh, you don't have a problem, why do you?
I agree they interpret, but you have to counter the argument with that reason. That's the only thing, because it is of, yeah. And that's why this best practice training, the awareness is actually is necessary to have all the genders together, which is.
It should not be your problem to answer them. They shouldn't be asking you this question, they should be answered by this general.
As you said, as you said, that the, these days everybody has a program around Women's Day. So that is because NAC has made it compulsory. So everybody has to take a photograph with a time and stamp. I think NAC should make 50% male attendance compulsory for this program.
Actually, I have a question on this. I mean, as you mentioned, don't you think that in all these activities, IUP, and all these activities, male should be brought in more and more because I mean, we need to learn, we need to educate ourselves about this.
Can I
Yes,
IUPAC women in
has a compulsory, yeah.
5-member country team has at least one male member.
Not in the first couple of years, after that it's been one.
So, yeah.
I mean, otherwise we'll be continuing to
No,
ask
see, even
such
if
idiotic
this-
questions forever.
Not to say that, but so even the Hyderabad meeting, Pressing for Progress, had about 20% male participation, which was there. And all these programs definitely have to be there. I should also, since you brought it up, I'll say that this, what she talked about, that in 2017, with a lot of effort, Prajwal Shastri established this working group. Even there, Sir Ram Ramaswamy played a very important role in doing a lot of backstage lobbying to get it done.
So I think it's on 4 and it's time to thank the speaker once again.
So I would like to thank both the speakers of this session, Professor Sukanya Sinha and Professor Sumati Rao, I would also like to thank Professor Shugato Ray for chairing this session. And now I request our Dean, Professor Rajiv Mitra, to kindly give a memento to Professor Shugato. So, so this brings us to the end of this session, and we are running fairly good on time. So we will now break for tea, and we will try to be back here by 4:15 because we have a panel discussion which starts exactly at 4:20. The panel discussion will run for about 1.5 hours. So please, let's try to be back at 4:50 for the panel discussion. Thank you. Forgot which topic. Sorry, opportunity is one, right?
So what is the challenges that we may
Yeah,
face?
challenges and opportunities for women in higher education and ways to overcome them. Challenges faced by women in higher education and ways to overcome them. And in order to moderate this session, I would like to request our director, Professor Tanushree Shahadas Gupta. So, Professor.
Okay. 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 I'm keeping you on phone. Okay. Yeah. Yes. Good afternoon, everyone. Sorry for this delay. So we have come up with an idea that she will join on Zoom. She can hear us perfectly, see us perfectly. The only problem is we cannot hear her. So she is on phone as well. So whenever she needs to talk, she will talk on phone and I will put it on the microphone. That's the best thing I can do. And so Rohini, of course, will be online. So other panelists, may I request them to come on stage? Professor Chandrima Shah. Professor Shubhra Chakraborty. Professor Vandana Nanal. And Professor Shuchetana Chatterjee. So I would first request 4 of you, and we will come to Rohini at the end because of this technical difficulty, to introduce yourself to the audience. You all have a microphone, so please. Yes, please.
Hi, I'm Vandana Nanal. I am a nuclear and accelerator physicist and experimental physicist by training. To keep it short, I have been associated with promoting the women in science. This is my passion for about 2 decades. I've been working on it. Currently, I am the chair of the Gender in Physics Working Group of IPA. I am a member of Association of Asia Pacific Physical Society Gender Group and also associated member of Working Group 5 of IUPAC.
Good afternoon, everyone. I'm Shubhra Chakraborty. I'm a person who is possibly a needle in a haystack, possibly. I'm sitting here and Chandrimati is beside me. Amongst all of you physicists, we have 2 biologists sitting here. I'm there in a National Institute of Plant Genome Research, which is a Department of Biotechnology Autonomous Institute. And currently I'm the director. I work in the area of everything related to plant biology and biotechnology. Regarding women in science, I think I was put into this from 2020, late 2020, early 2021, that Department of Biotechnology Secretary, Dean Secretary, Dr. Swaroop wanted to develop a database on women in science. And that was my kind of a first coming into really a women in science kind of activity. And I can tell about this later. And right now also I'm engaged. INSA put me after developing that, possibly thought maybe I'm the one person could do something, that is women in, means as a panel of women in science, and currently I'm chairing that committee. And that's all about me.
Hello, I'm Chandrima Shah. I have been associated with the National Institute of Immunology for more than 37 years, and I have served as director. And while being the director, I have initiated certain programs like Science Setu and all, where we have tried to engage young women into science. And then I've had a different administrative role as president of the Indian National Science Academy, where also we have, we didn't have a quota system, or we didn't want to have a quota system for to take in women, but we have in very subtle manners tried to increase the number of women in academies in India. And we have partially succeeded. I wouldn't say that we have succeeded very much. And I'm, as Shubha said, I'm a biologist, I'm not a physicist. So thank you very much.
Hello. So first of all, I would like to thank SNB and CBS and the organizing committee for having this wonderful conference, and my particular gratitude to Professor Tanushree Shah Dasgupta for inviting me at this occasion and giving me the platform to meet all of you and talk about this. So my name is Shuchetana Chatterjee, and I think I am like really the odd person out, because you can see all very senior physicists, biologists chairing big committees and directors of institutions. And Professor Shah Dasgupta thought that she has always been done that we need a young face, and I seem to be sometimes her favorite. So I am a faculty member at the School of Astrophysics at Presidency University, and I think you all saw my picture when Professor Rao showed the 2017 IPA, the first IPA GIPWG, the Gender Working Group in Physics, was established. And I was a member of that. And currently, I am actually a member of the ASI, the Astronomical Society of India, WGG, that is the working group on gender equity. And I was very, mesmerized with all the talks that was it was a great experience to hear all of you today. And many of the things I expect that we will discuss here were already discussed, but let's hope to have a very interesting session with all these distinguished people in the audience. Thank you.
Rohini, I think everyone knows you, but for the sake of consistency, may I request you to introduce yourself?
Yeah,
and you should
I shall
talk
do that. Can you hear me?
But already on phone call with me.
But
And
can you
we'll
hear
put
me?
the on the microphone.
Can
So
you hear
please
me
talk
through
on
Zoom?
phone.
No. Okay. So can you hear me now?
Yes, put it there.
Very good. Thank you for putting up with these vagaries of Zoom. I am, as I said again, I am I'm truly glad to be here. I just wish I could be there, because, when we began this whole story of women in STEM, through the entire set of sciences, there were so very few women that at that time we really thought that what we had to begin was just women in STEM. And imagine now that after, I don't know, something like 15, 20 years, we have actually a conference for women in quantum science and technology. You hear Suchetana talking about, the women in astronomy and so on and so forth. So I'm really thrilled. So to begin with, I am the superannuated professor of theoretical particle physics at Indian Institute of Science, and I have been there since 1992. And apart from science, as I already said, generally women in science is a subject very close to my heart. And there are all these doyens of women who are adorning the positions of directors, have adorned, and Chandrima particularly, who has been in fact the president of Indian National Science Academy. So I am very happy to be with you all, and I hope we have a great panel discussion.
Thank you. Thank you. I will go in the same order, and this will be question to all of you. You can just answer it one by one. Why did you choose to be a scientist? So maybe Vandana, we can start and we'll go in the same direction.
Yeah, this is a difficult question to answer because I think if I recall correctly, some at the school level itself, I was probably it was because of curiosity, which was there, and I had an interest in science and maths. It was fostered by my father, who himself did not have an opportunity to do any higher education, but he was very much interested in education and he was very supportive. And when I look back now, I think I couldn't have done anything other than science. So that's the only thing I probably know, whatever little bit I can do of. But yeah, I think it was more of a kind of a curiosity, always liked doing things, figuring it out, how it works.
So I think my interest in science grew when I was in class 8 student, and that was basically when we were taught Mendel genetics, first law and second law of Mendel. And at that time, we were taught that it seems there is something called gene. I didn't understand what is gene at that time. And it was said that chromosome harbors those, and it looks like a bit on a string. So possibly my curiosity was that how a gene can be looking like some bits on a string that we all wear. So that was possibly the curious moment for me to go into particularly not only science, but in biology. And that was my first thing that I came to science, and particularly in botany, that was later stage. But initially I wanted to study medicine, but being the single child and my father had a lot of problem with heart problem, so I didn't go there. So then it turned out to be that gene started with the experiment many of you may know, or if you remember your school days, on a plant only and the color of a flower. And therefore I thought that I should study the botany so that I would someday be able to see how a gene looks like. That was where I I was enthused to do science, and to be a scientist was not a thought when I was in a school, but I actually wanted to pursue as a scientist in a career that I would be basically telling you, which I was telling today morning to her. That was, we had a very great teacher, and that is Professor A.K. Sharma. Incidentally, this year is his birth centenary. And when I had a special paper, and he used to teach us cell biology and genetics, and he had a picture of Buddha. And in that picture, there used to be a quote, I'm quoting, it says, believe nothing merely because you have been told it, or because it is traditional, or because you yourself have imagined it. Do not believe what your teacher tells you merely out of respect for the teacher, but whatever after due examination and analysis you find to be conducive to the good, the benefit, the welfare of all beings, that doctrine believe and cling to and take it as your guide. I still carry this, and this is the last sentence possibly when we used to be sitting in those, as a student in front of Professor Sharma and behind that picture. And that possibly made me feel possibly to be a scientist would be a good profession.
It came very naturally to me because when I was very young, I don't know why, but I got very interested in insects, to the utter horror of my mother, because I used to collect them, bring them home, and sort of build a repository of insects. And but anyway, my father was very encouraging, and he bought me a microscope. He bought even a very primitive type of telescope. I got interested in looking at the stars and all. So interest in science was generated then and there, and eventually my mother also accepted this, and both of them encouraged me. So the primary thing was encouragement from my parents to go into science, and also my teachers in school. They were very supportive. I had many choices to go in different professions because I was the vice captain of the Bengal women's cricket team. I mean, the initial days of women's cricket. And, I interest in science over that. And so eventually, that's how I came into science and continued studying science.
Yeah, my story is sort of simple because my father he's actually a professor of physics. And so, I mean, I really loved doing mathematics, but then there was like a mandate that I had to give my best to become a physicist. So that, I mean, I have to study science. It was like a mandate. You don't have any other option. But anyway, I really loved science. And yeah, I think I had real passion about the night sky because I grew up in a suburban town, and at those time in Berhampur where I grew up, the night sky was much better than how it is now. Now there's a lot of light pollution. And I remember that the sun is our nearest star, and the second nearest star is, it's Proxima Centauri and all that. So I wanted to become an astronomer. I didn't understand what it meant, but yeah. So that's how science came to be. Thank you. Rohini, I hope you can hear. So could you share your version? Rohini, can you hear us? You have to speak on phone. I cannot hear you.
Can you hear me now?
Can you speak on phone, please?
Yeah, I am speaking on phone. Let me start the call again to you. I'm switching it off and making a call to you.
We can hear you. We can hear you, Rohini.
Oh, now you can hear me. Good.
Yeah, yeah.
So, okay, I should tell you that my story is quite different from all my friends. And since Chandrima is about the same age as me, I cannot say younger, but all the others are younger. In fact, actually, I'll tell you something. I grew up in a very typical Maharashtrian family where there were not even engineers and doctors. I mean, there were a few lawyers and maybe one or two doctors. So science was, in fact, I grew up in in an environment which taught me, typical what you would put at high stake in a typical British school. I learned literature. I discussed literature extensively. But I think what my parents did, both of them who were not science people, they taught me how to be an intellectual, how to treasure things that are intellectual. But actually, I went to this girls' high school where I didn't even study science till my 10th grade. So, 7th grade. And I studied, very little science in my school, read very few books. But my only insistence was that there was a state level scholarship examination in my 7th grade. And I wanted to get it because in my school, nobody was ever getting it. And in fact, as it turned out, there was good reason. There was a paper in science, and we were not studying science till 7th grade. So my teachers, school teachers, actually took time out on weekends and they taught me science. That was the first time I got introduced to the world of science. And I read some Marathi the magazines, which one heard, these magazines, which were, articles in science in Marathi. Then the next step was really the National Science Talent Search Scholarship. So, I mean, just to tell you, I initially thought I was going to be a Sanskrit scholar. Then I thought I was going to be a mathematician because I loved mathematics. And then very, very, intelligently in my mind, I said that I will study physics because physics gives me a higher opportunity to get a job. But then the important thing was the National Science Talent Scholarship, which was a very primitive avatar of what is called KVPY. And that opened my world, my eyes to the world of science. Then I read lives of people like Marie Curie, lives of people like Tesla, Nikola Tesla. And that is where I understood that science is something, a wonderful vista that you want to follow. And in fact, last but not the least, when I got the Science Talent Scholarship, because of that, I could actually study in Indian Institute of Technology, Bombay, because otherwise my parents would not have been able to afford to keep me out of town. And there I met a wonderful teacher. His name was Professor Patil. And he opened completely new world of theoretical physics. Even in his problems, he gave us, I think, once a problem, and I did that, and I realized that science is as much a description of nature, as much a creation of your mind. And this combination, that human mind can in fact, reach out for something, the secrets of nature through thinking and experimentation, was a revelation. And I think after that, there was no looking back. Theoretical physics was it. And I think I have never once regretted doing that or choosing that.
Thank you, Rohini. Thanks a lot. I will now move back to Shuchetana, who is the youngest person here. So I think in our conference, we have several talks like role models. So what is your experience? What is really the role of role model?
Yeah, I think the role of role model is immense. For example, I think I was resonating with Dr. Shukarna Sinha's talk when she said that there was this gender reversal. I mean, in my home, my dad did not used to do any household work. I don't think he ever spoke with masons or anybody. That was totally done by my mom. She used to, you fix screwdrivers. You have to do some, they fix some building stuff. I remember that when I was in 4th grade, my mom and my uncle, my mother's brother, they sort of made a little bit staircase so that this is an old house and, there were issues. So, there is this gender stereotyping was never there. And my mother is a very independent, she's very strongly feminist and very independent. And the other role model who had a lot of influence on me is my maternal grandmother. So my mom's mom, she was both, but looking, when I grew up looking at these very independent and strong women, none of them were working, but the independence, the strong personality, that I think played a lot of role that, you should never give up in life, no matter what happens, you should move forward. And all the support, it's not just my mom and grandmother. I think family, we spoke about how family matters. In my case, my family was super supportive, and particularly my mother, she got married at an early age, and she always wanted that. I just want my daughters to be very independent and strong women in life. She was a very strong woman, and so there was so strong encouragement from the family that you must fulfill your dream and work hard. So I think the role model matters very much. And then, of course, I had tremendous, teachers in school, in college, during my PhD, and even now my students, all of them seem to always inspire me to try to work hard and take challenges. I think that's very important. So it's very, very important. But the key role models, I think I would give the credit to my mom and grandma. Yeah.
Thank you so much. I think we will return back to two of our biologists in the panel. So has your gender affected your career in biology? First Chandrima, then Shubhra.
I don't think it has interfered, this gender has interfered with my, being a biologist or being a scientist for that matter. I mean, there will always, after you become a scientist, there are things that very subtle things come about that you can only perceive yourself. Otherwise, I don't think my gender has had anything to do. And all these things, your hard work, your sincerity, it has no gender to them. So.
So I think I would echo Chandrimadi. So in my career also, I have never ever thought that gender was any issue. But only thing is that I should go back to my childhood when I was in school, and that I cannot blame. But it's actually, as I said, I was the only child, and my father had the first heart attack when I was in class 1, and third when the day I was actually signing the admit card for the 10th board exam. And therefore, because I was the only child, he thought that I should study up to 12, that's maximum, and then I should get married and get settled, because that came from his within that how long he would be there and then what happens. But that was something somewhere I actually, but one way, since I was a single child, whatever I said to him, he never said no. But he used to talk to my mother thinking that I'm sleeping at night. And maybe I overheard many things, and that was one thing that I did not sit for joint, although I filled the form because I heard that he's telling. So I would say that was a time, my going to the college, going to the university, that some kind of thing, because my father's elder brother, although is a pass out from Jadavpur during Jiguna Sen's time and was very highly career oriented person, but somehow I come from very conservative family. So where they all believed, all brothers believed that all we are two sister, one brother. So my brother was allowed to go to IIT Kharagpur, but my uncle's daughter was sent to a home science college in Kolkata. And what my father did, all throughout, I was sent to a girls' school in Unit Missionary and Kamala Girls' School here. And after that, he wanted me to study in Brabant because again, another women's school, because they were not very confident that should I go to a poet. But in any case, I was helped by, we were three very good friends in Kamala Girls. So one of my friends' mother actually got me the form for Presidency College. I didn't tell my father, not even in my house, filled it and submitted. So that was something that I, for some time, in my family that happened, but I must tell here, sitting in SN Bose. So what happened, I gave the exam for presidency, the result came out, and one of my grandmother, whose son was very familiar in this audience, whose name is Jayanta Bhattacharya, popularly known as JKB, my uncle. And I still remember that I came seeing the result from presidency and going up at house, and he is entering. And he asked my grandmother what happened to her. I have a family oriented name. So my grandmother said she got into. Then he said, when my other father and other uncle is saying I should not go, and he said, now you people should not look back about her. So it's all done. She got into. But my father put me into Ashutosh College in economics department because he had a friend's brother who was the head of the department in economics in Ashutosh, and I was put into his hand to go to Jogomaya to do economics so that I can return back by lunch, have a lunch proper and sleep. And after, in any case, I'm studying just for the sake of studying, and he's looking for somebody, whether I should be married and get into. So that was my story. But thereafter, when I got into, again, I got all support, and in future career, I never would need to look back. And everywhere, somehow I was a lucky person possibly. So I never had any hurdle.
So now, of course, your career in physics, there are 3 physicists, and Vandana, you can start.
So I come from a very conventional lower middle class family. Even I studied throughout in my government school and on the scholarship. It's just that my parents are very motivated and they put us, they went through a lot of hardship to put us there. So at home, if it was not for my father's support, I don't think I would have been able to do anything unconventional, because it was a problem that I didn't do all the things which as a girl I was supposed to do. I was expected to do the things, I didn't do it. But he would have liked me to be a doctor or a mathematician, so I didn't do either of the things. I don't know, but yeah, so he felt that I had capability, or he always felt we should do whatever we want to do, we should excel. It didn't matter to him what we decide to do. And that was one thing, that was the motto which he always put on that he said, you can do anything. जाके जूता भी बनाओ तो मुझे कोई problem नहीं है, but ऐसे बनाओ कि सब लोग देखते रह जाने चाहिए. So that was the thing which was there. So I think the choice was difficult. What I wanted to do was difficult. Then I did further thing was I went to MSc for Pune TI for MSc course. At that time, my father was already diagnosed with cancer, and the future was very uncertain and bleak. But he was like, You want to study, you study. I have not put any burden on you. You go on your own strength, on your scholarship. You want to go anywhere. It was actually one thing which I should perhaps say was that when I was in ninth standard in school, I went to a Marathi girls' school. So the Marathi Vigyan Parishad, Professor V.G. Kulkarni, who founded Omi Baba Center of Science Education, he had organized a visit through Marathi Vigyan Parishad. So that was my first visit to TIFR in 1979. And I was, of course, very much impressed. But at that time, I didn't think that I will come back to TIFR to work. But that was sort of, that was my first view of seeing what else science or scientist life would be. Now, so so making a choice for the career was difficult, but I think it happened with that. And of course, I had along with that some of few other good teachers who helped me with that. I certainly think the gender mattered in the progression of the career, even if it did not matter in the choice. I'm an experimentalist. I work in an accelerator physics. You always work with a group of people. So one is your colleague, other is also you interact with a lot of different level staff who come from many different parts of the society, and for most of them, accepting a woman voice has been a problem. So it has been a lot of struggle in the last 2 decades, and I think it also makes one, okay, maybe that's my excuse, but at least I would say for my side that it has been overly aggressive in many cases. Because you feel you're not heard, you get aggressive, and then after a while it becomes a habit, you don't realize. So that's one thing which has definitely made a difference. And it's also, I have found even with students, because it's not just the boys, even with girl students, for them, if there is a male colleague telling them something and if I'm telling something, I found that it's more, they are more likely to take a criticism from a male colleague than. So this is also another thing which I felt. So that's what I mean by that it affects in the progression in the country.
Yeah, so I think as our other colleagues put up, so family wise, there was only one incident because I was the first, so my family lived in that Berhampur town and in the Murshidabad district for like 5 generations. And I was the first person in the family to go abroad. So my parents and some people they were very proud that, you know, she's going for a scholarship for a PhD. But my grandfather, this is my dad's dad, he was very sad that, oh, you know, you will never return back to India. Oh, is it okay to send a girl outside of this country? So I think that's the only occasion family wise. In the family, I don't think it ever mattered. Professionally, when I was a student, I didn't even know that a gender issue exists in physics. When I was an undergraduate and master's student, when I went to the US, as many others said, in a graduate school, I felt that gender is an issue. I had tremendously supportive male colleagues. All my mentors, my advisor, postdoc mentors, all were male. They were all very supportive. But I think in one kind of aspect, I felt my gender mattered, and that was since it's a very male-dominated field, the culture of the field, like how the physicists socialize in a conference. I mean, it's a very sort of male psyche dominates the culture of the field, that how you should behave as a physicist is so much determined by how men behave among themselves, how men socialize. So one way I tried to cope up with just by trying to, I think I saw one in Professor Rupamanjari Ghosh's talk, that I started behaving like men, that, you know, I have to speak very loudly so that I get heard. Because my voice must be very loud. So sort of that thing was very implicit. But then, and when I think after I took a job in Presidency University, what I found is that as a student, people treat you differently. But when you become a colleague and you are a competitor, in some sense, you are a competitor. I think Professor Nanal was mentioning that taking a woman as a boss, they are still not. I think a woman has a voice. She has an opinion. She could be very strong. She could just refute me in 5 minutes. These things are still not fully accepted by the society, and our colleagues, both male and female, in the physics community, I'm saying, they are coming from the society. So they are all part of it, consciously or unconsciously. So yeah, that's where the gender definitely mattered. not that it hindered my progress or anything, but you still really feel that people are still not ready to think that a woman can be so aggressive. She cannot have children and she can stay like at 11 o'clock in the night and write her paper. That's too aggressive for a 36-year woman to do. I think I have felt that. Yeah.
Thanks, Suchitana. So, Rohini, are you still on the call? Would you like to add something on this? Yeah, we can hear you.
Again, I think, I don't know the experiences that you had, but I was born in this, and not because of that I used to. But I literally get that one of the class, or I sort of nowhere, protected. So, okay, I think, I should go to that's it one. Or to the people around. I tried to ask my friend whether it was just a book that I had, but I think when my classmate and I had that there was no problem. But I will give you both the examples. Here's what I call unbiased mental happen. And you can take for yourself, learn from it or conclude from it, whether the gender indirectly affects sometimes the gender. So, first example is my favorite teacher from the party, whom I told you about, and who liked me, who actually thought that I was doing quite well. But I was supposed to go to the US to do my PhD, and it was 1974. So at which point I said, why do you want to go abroad? You'll find a very good advisor here, for a single girl, young girl to be in the US. It's not right. And my younger, junior was male. And he had the same credentials as I did. Both of us did our own information. Both of us went off of the class. And he told him, I just go abroad to widen your own. But instead of a student, instead of it quite often, but instead of a student, I went abroad. My younger junior friend actually stayed in here for an exhibition. I think both of us really had a success. So if I go back, I don't thought of it as that much. But now I think that my gender must have affected out of affection, out of care, that vice versa. But that was okay. I mean, that I am able to do it. I could be, I was confident I could do it. But now I will give you two examples of, again, this indirect bias because I cannot put information at the door of the community diapers. Because when I was a young postdoctor, and one of my friends, whom I went on to write many important papers, great friends, great collaborators. But I remember, after 2 years of my business job, mind you, well, two papers in clinical better. So, it was not that. But he told me, oh, I never realized you were serious, so serious about that. So this is just the ingrained that oh, I need to be serious about that. I mean, it's was one example. And the second one, I thought the same was not so particularly good. Because again, after my experience in the Tata Institute, I was, all of us young people, we're trying to see where we get a job. And he told me, your best bet is to get a job in a women's college, in a city. So, in our job, it was not very common then, in a very competitive subject. Because then I can read my agreement. Not unfortunately, that maybe thought I was not a good scientist. But this level of lowering of the expectation is not something that I can answer. You can understand, okay, you are not good enough for a research career, you are not good enough for IIT. Then maybe you are required to bring yourself up. But the women's college in a local area is something that I think is sort of, how many layers go. And if I had taken this comment to heart, you wouldn't be seeing me. So now, all I can say, I do not think that I saw a gender discrimination in something. It wasn't so that I didn't get something because I was a woman. I'm not sure. I'm sorry to say you. And the decisions about, the committees and whatnot, they are not affected by the biases that we have. And these are the indirect biases of us. That's all I can say. And I think, if it could be more prevalent in physics or less in biology, I don't know. But on the other hand, I can still say that the percentage of successful women scientists of the women who train is not very different more successful and work anyway. Maybe slightly higher for biology. So I am not particularly sure that these internal biases do not affect and impact the journey. It's not something that you can see, not something you can quantify, but I believe that this is this unwritten biases, invisible biases. Thank you very much.
Thank you. So thank you, Rohini. In spite of all this technical problem, we could at least get something out of you. Now, since we have in our panel few biologists and few physicists, there is a stereotype problem. If we really see the statistics, we see relatively more women in biology compared to physics. So maybe Chandrima, you first. Is there a reason for it? It's a definite pattern all over the world. It's true.
See, it's the thing is that in biology, it's true that you have more women. One of the reasons about, as I can see in my environs, that the girls are usually encouraged to take up subjects which are not like mathematics and physics. That happens from home also. That happens at school. Teachers are telling, students to take up subjects like biology and not physics and mathematics, which are more calculated or more, I think they perceive it as difficult subjects. So I think that is one of the reasons, because that is happening at sort of grassroots of our education. And then as you go up, then the filter, also takes care of some. And eventually you end up with having more biology-oriented students than physics or mathematics, or even chemistry for that matter. I would say, even in medicine, women are doing very well. There are many women in medicine, but not in engineering. Physics yourself, is the worst. So I think it's the conditioning from the family, social conditioning later on. So all this is leading to larger mass in biology, biology is not an easy subject. I mean, now with interdisciplinarity, it has become a very, very complicated subject. But that realization is not there.
Thank you. Shubhra, you would like to add something?
I think I would agree some part with Chandravati, what she is saying, maybe that one part, but I really don't know. Since it is a general seeing, and it is true for ages and across country, across globe. So I sometimes feel that now neuroscience has come up in such a way, I don't know really how our brains are wired, whether we really have kind of a wiring in the brain of a male versus a female, that female brain actually tells us that you study biology or medicine rather than going for engineering or, physics or chemistry or mathematics. That's one aspect which I really am inquisitive of. So I hope some neuroscientists someday would come up with this. But one thing also, not only that our environment, but also sometimes I feel, women are more, I would say, what should I say? Women are more towards, life or kind of a on softer way, as well as more close to the nature. So if you are more close to the nature and kind of thing, so possibly that makes you towards inclination into understanding biological problems and the biology, rather than the boys or male who are mostly, if you see normally, boys are otherwise they are more inclined to uh, different sorts of activities from the childhood. So I really don't know, but I strongly believe there must be something which is with our brain, and that should be actually, uh, you know, that story has to be somehow told, and someday we would know about it.
I think Vandana wants to add something. I just want to make
a comment. Number of women in medicine is actually unusually high in India compared to the global comparison. A part of that is because in Indian society, women and children prefer to go to the women doctors. But again, if you see, it is more at a general practice level, at a specialization and a higher level for men also. The other observation which I have seen is it's kind of a positive feedback system. When the young girls are choosing a career, it's like 10 other friends are doing a particular subject and the other ones only, there are only few women. So it also adds up to the thing is what I feel. So that like when we were in college, for example, in our class, was in my BSc class, we were 14 girls out of 40, which was very, very unusual. It has always been the number was 3, 4. But in the same year, in biology, there was a class of 20, there was one boy. So it was the 19 one number in the class of biology. So it was like more like, the way the people are like, which subject to choose, or even parents feel comfortable in doing that. So that observation also, with that influences. But it's also often said that physics and maths are perceived as a difficult subject. But then this surprisingly in physics, the gender fraction is worse than that in maths. And that again is true there, but in India it is particularly.
Yes. I think we will move to some other question that I will ask Shubhra, because all of us, you are also mother and you are raising your kids. So for a women scientist, how difficult it is to make the work-life balance, and given the fact still raising the kids is mother's responsibility primarily. I think it was said that whether the all the male faculties, they don't have children, it's only the female who have children. So what would be your take on this?
So first of all, I would again say I am a lucky mother because I have a very supporting mother. And all throughout, I think in my career, I told you about my father and uncle's view about a girl to go to a college. But all throughout, my mother was very much supportive to me, saying that maybe because she never got that kind of opportunity. She is always a homemaker, and she always thought that I should stand on my own feet. And she was always supportive. When even my father didn't want me to go out from Calcutta to Delhi to do PhD, but my mother supported, and also my grandmother that I talked about. So these two lady actually shaped my all career and my everything. I'm not saying that my father or others did not do. Yes, they also have influence. But when I got my daughter, by the time my father was no more, my mother again was staying with us, and that was a great support. So honestly speaking, means possibly my daughter is more attached to my mother than to me. And that was a great support for me, which many of the women do not get in their life. But nonetheless, I had difficult times when my mother was not well. When my mother was in Calcutta, I was in Delhi. My child was very small, and like I used to work in lab even in late night. Even I became faculty, so I used to keep her in a creche that our institute was incubated in JNU those days, and we had a small creche near our institute within the JNU campus. So I used to keep her there. It's difficult, but we used to stay within the campus. So staying inside the campus also helped me to make this balance between, making my daughter grow up, at the same time seeing that my initial projects coming up, my first student is making her his thesis or her thesis. At the same time, my daughter is going possibly to growing up and not even in the school, but in the kids' school. So that way I was lucky, but otherwise it's difficult. But one can take out time. So I used to work when she sleeps, and then my time starts. So something like that. And I always like cooking. I still cook every day, at least one dish. So that's where I think all my tiredness goes from me. And so it's difficult, but it is manageable when you have a supportive family. At the same time, I must say my husband also in the same field, and somehow it helped because they understand then what you are doing. And so these are all the things. So I never had such very difficult situation. Sometimes I see even one of my students had that kind of a very difficult situation. Came from a background of a Haryana family who are very conservative. But those kind of things I never had in my life. But nonetheless, doing the work and home balance, it's really a challenge for any women, and we have to come up with that, and we do that.
Thank you. Now a question to Vandana, that, the safety issues, because you said all the fathers were very protective, family were protective, because they were concerned about the safety of their girl child. And this concern is not unsubstantiated, because of course things happen and unpleasant thing happens. So of course there is now ICC, it was mentioned. So many measures has been taken, but still, do you think that the situation can be improved, or if it can be improved, how it can be improved?
Yeah, certainly, I think the things are getting better, but there is a lot of scope for improvement. We mentioned about this summer school, which we have started program. So I will just cite something from that. So typically we select 40 students, and in the first 2 years, the program was online because of COVID. So there was no issue. The next 2 years, we had in-person program there. Last year also, we had about 10 students out of 40, 10 out of 40, about 25% were traveling long distance for the first time in their life. And some of them had to convince their parents very hard to let them come to Bombay to do this program. So this again is related to the safety. And so one of them, I mean, sometimes what helps is now they form a group together so that people who are coming from same region travel together. Because of the phone, the connectivity is better. But I think what will help really is that hygiene conditions at various places as well as during the travel have to improve. The safety security definitely has to improve because that also gives parents a certain confidence. And apart from ICC, overall training on what is permissible, what is not permissible, what is the friendly gesture, and where the friendly gesture should stop, a friendly interaction should stop, that in the community. That aspect also needs to be improved. This other, in addition to that, I mean, when they come to a place like TIFR, of course, everything is under CCTV surveillance, and these places are really safe, and it's an all-women program. So it's yeah. But they also, I mean, students, once they come to the city, they are not under like a normal hostel lock and key. So they go out. Last year we had this problem that 7, 8 girls went out and came back at 2 o'clock in the night. So we just sort of tell them you should know what you're going to and where they're there. We don't forbid that. So this is also happens because if they just come out completely without knowledge, they do it. So I think it's the increasing awareness and systematic improvement. That is both the things are equally essential.
I think before we open the thing to the audience, I would just like to ask all of you, one by one, if you could change one or two things to increase the proportion of women in science, what you would suggest? Maybe we start from Chandrima.
As I said that at the family level, at the school level, girl child has to be encouraged. But I think if you come up higher, I have seen that there is a hiring difficulty because of impending maternity leaves, because of the 2-year child care leave. That it actually deters people to take a woman into their projects because their 2.5 years are gone. So, if I'm given a choice, I would change that thing in the sense that you give 1 year to the woman for childcare, 1 year to the man for the childcare. So, so when you're hiring, you know that you have to give the man also 1 year off. And that way we can level a lot of this hiring problems at the higher level. But as I said, that this conditioning has to be there and parents need to educate themselves to initiate their child into science, or for that matter, many of the parents don't have a solid career or don't want their girl child to have a solid career. Not only science, I'm saying anything, but so I think it's a holistic problem, but if you can change this child care thing, a lot of hiring will be there.
So I agree with Chandramati, but I would add on to that, that not only for these 2 years, 1 year, 1 year, but even the maternity leave that women get, we were here, if you remember Chandramati, during that Swati launch, someone was telling that there is a country, I forgot the name of the country, where they give equal number of months for a maternity leave as well as equal number of paternity leave. So that is also one more thing that should be done here as well, which will do a level play. What I feel is that, now if you look into, there is also a kind of a difference that you see in different states in India, because when we get students from different states in the institute, there are differences. If you start talking to the student that how their family think about their career, there are differences. So this is one. Second is that if you think about the girl students coming in a career from the metro cities like Calcutta, Bombay, Madras, Bangalore, Hyderabad, it's a very different socio-economic status right now, not like earlier. So you still get more girl student coming into science or any other profession. But we need to look into the villages, we need to look into the tier 2 cities, tier 3 cities, where we need to start inculcating somehow from the school level, talking to, maybe I don't know how it is possible, but talking to parents with the community level. From there, it has to come that girl students should be sent to school, should be going to the college, should have their own career, should be economically independent. So that's more of a challenge, at least in India, that I feel. And that is where somewhere
somebody needs to look into from the school level? I would suggest two things. One is gender metric, gender audit. At every stage, publish the numbers. These numbers should stay in the this, be it for the school, be it for the college, be it whatever is there. Once the numbers start staying, and everybody, if it is become mandatory, we take all the financial audits so seriously. So we should take gender audit seriously and publish it. It will help in, once the numbers are there, then nobody can deny it. Because the data is there. So that is one thing. The second thing I would like to change is the image which we have. Many times, even today, we have an image of a woman doing a certain thing. So that definitely needs breaking. So, like I was just telling somebody, I think you should have textbooks which feature a woman driving a scooter and a husband carrying a kid behind or fixing the things that it should be there. And here the social media plays a big role. We all have film stars advertising for Santro, so we go to buy Santro, right? So this is where we should have advertised in terms of different careers for coming for the woman. Because I will just give me a 30 seconds, I'll tell you that I know that there's this movie on Mangalyaan where it's shown that the lead character gets the bright idea while making the puris. And this is also kind of showcased. While I can appreciate that people like cooking and can enjoy cooking and should do it if they want, but this movies in particularly stereotype what a woman should be doing it. And this kind of things have to be avoided.
Okay, so I think there are multiple layers to it. So what some of our panelists spoke is about school level and family level. So that's sort of the stereotyping and social level where we can play some roles, but we cannot play the leading role. So the leading role where we can play really make a difference is in our professional spaces, because society is a very big thing. It's just we can of course go and make 2 workshops in school, but I would like to say that if we look at the fraction of women, girls, students in school, the ratio of boys and girls are almost equal. Even it's equal at the level of masters. At PhD, there is a drop, but it drops as you go to higher and higher levels. That's one important point. The other important point is it also differs from discipline to discipline. So in biology, it's different. In physics, it's different. In computer science, it's different. So just society and school and family is not the cause. There is also initiatives that has to be taken at the institutional level. And I think the gender audit that Professor Nanal said is very important. You always put the thing on everybody's face. Only awareness can just raise awareness. The other thing I like to say, it is a philosophical statement, but that can also, take practical shapes, is that institutions must not feel that hiring a woman or hiring somebody from the marginalized section of the society is just a diversity rectification issue. They should look at women, let's talk in the context of gender. They should look at women, hiring women is not just rectifying that we have to address this diversity issue. It is actually enriching our program, as Professor Bomanjuriko said, that the more diverse a population, you have more creativity there, you have more productivity there. So hiring women is actually enriching our discipline or our department or our institution. That should be the way to go. And the only way we can ensure that is by having workshops like this, having public discussions like this, having our social media views about this, that this is not just a question of morality or equity or some policy that the government has told that we have to implement. This is about our own good. Physics will do better if we have the entire section of society participating in it. Biology will be better. Our human history, our human future will be better if we have talent from all sections of the society. We just can't ignore 70% of the population and have a very small fraction of the society, coming into a program. So I think that's the policy. I would say that it should be celebrated as a very rich thing.
Rohini, I hope you can still listen us. So we will have you say the last word on this and before we go to the audience.
Okay, thank you very much. As it happens, I think all my colleagues on the dais have touched upon many various majors we face, and that was pointed out very clearly by Jasma, I like that. That the majors we implement for making level playing should not be affected by our biases about what is good for women. I just give you an example that if a good mentor is trying to, advise the couple, both of it are his or her sisters. Now when he's the elder, the boy is the elder one, and very often people kind of say, yeah, maybe for the sake of family, there's a moment you might actually expect a lower position, a not money position. And you move them out. Because once you start behind the line, don't start at the succeed line. So I'm proud to, do at least be behind. And then you need enormous dedication, enormous effort to get ahead by some. So Ali, as I said in the morning, we are really happy that there are a lot of papers and lot of majors that are putting. One of the things that we must do is that what all major governments put in to the percentage of sciences in general, what the percentage of pure sciences, should actually look at the special needs of women. And in fact, I think the first step has been taken. In that, the national 2020 Science, Technology and Women for Innovative Policy. Yes. Include this for example, as the Chipana pointed out together. Yes, inclusion. On the whole, it benefits the society and work with them. So therefore, I think this is more progress forward for the institution, the scientific society, ourselves, the society of us, have to perform their own audit, their own analysis, and have to get rid of stereotypes that we have. Thank you very much.
Thank you, Rohini. Thanks a lot. So with that, I think panelists already have shared all their views, but I see in the audience there are many experienced people. So if you would like to add anything, please. Or even, some specific question or whatever. Because I'm sure on all the points we discussed, you also have maybe a slightly different point take, or I don't know, maybe you will agree with whatever the panelist has said. So please. Ravala, here. Okay, please.
Hello. I've listened to the panelist comments and suggestions.
Can you please introduce yourself? That will be very nice.
Sure. I'm Monimala Dash. I used to teach physics in Presidency College for a long time. Thereafter, I moved to academic administration. And I did my PhD from Cavendish Laboratory many years back. And I also did my postdoctoral fellowship from USA. From my experience of working in India, that's for about 4 years. And I worked with men as well as women's institutions also. Regarding women or having more women in science, my suggestion would be making these women scientists visible to young girls. In school level and at college level will be very, very encouraging because they are dependent people, they are never sure. Most of them are still not sure. And even from the general side, the physics means they will be BSc students. They have to take up science in their school and then continue in the college. And nowadays with the 4-year undergraduate course, it is quite rigorous. With 2 exams every year. And it is quite rigorous. And they may drop off, they may not complete the 4 years. I have this anxiety, this possibility it might happen. Quite a few will drop off in the 3rd year with a general degree and not an honors degree. And the rigorous hard work necessary to have a career in physics, it's a very long career. You don't start earning very early. There is a very good scholarship. I mean, if you get a scholarship, it's all right, it sustains yourself, but still, to become a faculty, they're never sure. I know of an inspired fellow who hasn't got a permanent position, and she's worried about when and where she will get it. So these are anxiety for young people, young women, and again, that point of having the spouse working in the same town or same city. I'm not talking about the same institution, but in the same city at least. That's not always possible. So these difficulties are there, and the kind of the conversation I listened to since this morning is very enlightening, it's supporting, and this kind of conversation should be heard by those young people. So connecting to school students and college students is very, very important. And I forget, but one of the panelists mentioned that mentoring young PhDs, I think Professor Goldmuller who said, mentoring young women PhDs so that they don't drop off, so they don't take up just any job and they remain in academics. That is what is necessary. And I think it's a women scientist obligation to the society and to the younger women. So they come in and join us. Thank you very much.
I just have a question for you all at the top level, when you are sitting in the policy making level, or you're in the level where you can suggest various pointers to the policy making. What are the challenges for the suggestions to turn into executions and, to convert it into, let's say we have a set of suggestions now and you decide to take it up further, then what is it that's the roadblock? What do you think is the roadblock to execute some policies that you might want to?
Yeah, I can give just, anyone please take on, yeah.
As per my experience, I think once you suggest, I think having more women in these policy making bodies that is one help. And so that they are sensitive to the women's cause. One is that, but my experience has been that it takes an incredibly long time. It takes place though, because if you look at DST, I mean, having their problems like they have the program Gati means that, every institution should have X amount of women. I mean, that's a kind of, that is not really fructified into reality, but they have got that program. That is after a lot of debate. And all the DST schemes that you see, the women-friendly schemes, they took long time to get implemented. So this is one problem. Now, why that happens, I don't think it is because just men are sitting there and women are not sitting there. I think it's just our system.
Yes,
Our system.
I think that was exactly my point of view, that it's a systematic thing, that it takes long time. But eventually it happens if we keep pushing and, stay very focused to it. That's what my experience says, that if you have a good thing to push, you have to push hard. It takes time, but it's not because women or men discrimination. That's what
I would just like to add, I don't think there is really any kind of hindrance. It's just your system is slow, very rightly mentioned. But you can see that government is proactive. They have taken it very seriously. That's the reason you have so many different power schemes, Kiran, one after another scheme. Why that has happened? Because government has taken it seriously. So the message has been conveyed. You might say it took them several years to, finally implement it. But the message, they read it. But I think I really liked Vandana's suggestion. If there is a kind of gender auditing, for example, there was a suggestion, every institute in their homepage itself, they give these gender statistics. It was very difficult to implement. People didn't agree to it. I don't know why, but people didn't.
Even for conferences, it should be.
Yeah, even for conferences, but those kind of things, putting hard numbers, people are hesitant because they feel they will be blamed that we are not doing the
And many
justice.
people are not doing it.
Yeah.
But anyway, if you look back to the last 10 years before, what was the situation? And 10 years after today, what is the situation? There are many schemes, not only from DST, TBT biocare scheme is there. There are schemes from CSR. There are schemes from other funding agencies where there are lot of scope where women, even DST, that women science scheme for ABC. So women can go up to the age of maybe 55 in their career, may not be a permanent job, but still those avenues have been created. Now, the concern is that yes, process is slow. That's not only in the women's scheme, but I would say even if you think a project grant, and in that case, let's say coming from a DBT institution, so if you write any project in Department of Biotechnology, even in DST, you don't get the funding before 1 year, right? So in that case, we are slow in our thinking, whether it is a women related issue or it is a general issue. So we need to change that if we want to bring a change. We have to move fast. So the change has to come overall, not only to a women specific scheme. That's what I feel. But at the same time, I would say we are progressing, and there are things that we CSCRB gives grants now in 6 months possibly. So changes are happening, and I'm hopeful that there will be better changes and better days in front of us.
Rohini, would you like to add anything? I could not follow. Rohini, there is lot of echo. We cannot hear you.
The other
It's
mic,
better.
you switch off the other microscope, microphone.
Can you try again?
Yeah, can you hear me better now?
Yes.
Yeah. What I want to say is that you have a very lot of current clips and it's certainly much better than it was 20 years ago. Oh, I cannot be happy. It is necessary, but it is not sufficient. The other important aspect is empowerment. The super one important time for professors have to internalize the concept of gender neutrality. I don't want to say gender neutrality. And you put let this thing time, let it go their own way. And everyone says this is very long, the process is very slow. And I was pleased to, with a small expression, I have done some of that. For the World Academy of Sciences, so and the estimate during scientific papers, what is the estimate on this? But that's all as women fellow. Wow, the World Academy. So I do not talk about good things, that and I found that by writing the molecular process, the business, I was really supporting that. So, some to property makers are required also know what we are. As said, along with it, a general, I think that's what you consider as well, a general awareness, a general, understanding of the human world. And that's the gift to touch the thing that they are. And if somebody is clearly answers for the audience, what is the problem with looking for the future state? I have not been director or any, I have not made any here my friends or I have done that and they are exposed. But I know that if we analyze the need of policy implementation,
Thank you, Rohini. Sorry, I can see you are putting lot of effort because speaking on phone with this is very difficult. And I know you are not well, but thank you so much, putting so much effort. Vandana, you wanted to
Yeah,
add?
I want to make a couple of quick points. About the policy also. See, as was pointed out earlier in the talks, that now this is also something which has been identified as an area by United Nations. So there is also global pressure coming from there universally, and this also will have an impact on the government policies. Of course, the one thing which we have to be careful with government policies is, I mean, the policies are good, the implementation doesn't get that well done. There are many slip between cup and lip. So that needs to improve in India. But that's I think the overall increase coming from the global factor also will help. Second thing was also mentioned that even for conferences, we don't have a gender data, which is important. So one of the ways which we can help in getting this is wherever we participate in conferences, get these numbers and try to put it together. There is also this Bias Watch India now, which does this work. On the more positive side, I would say, at least for all the national symposia, we have tried to do this last year for the energy physics, nuclear physics, and the other meetings. Let's try to have this some session related to the gender awareness efforts in all the national conferences. Again, it helps in creating awareness and going further. That's all I would like.
Anjana, I think she wanted to say something.
Yeah, thank you, Tanushree. Am I audible? So, Anjana Devi from the Leibniz Institute for Solid State and Materials Research and TU Dresden. So I just wanted to add a couple of things. One is that awareness, you all talked about it. I just want to give an example. In the Department of Physics, where I formerly was, we had hardly any women in the physics department, okay? Then they were recruiting people, always, it was always men. And at some stage, the rector said, you have to have one woman. Otherwise, we're not going to recruit, okay? So he was bent upon that. And then I was in the committee too, okay? So this was the condition he put, otherwise we will not hire. Let the chair be vacant. And it was. It was after a famous physicist, actually he's working in the field of magnetism. Okay? So that's one thing. And now they have come up with a rule, at least 30% of the position should be filled by women. And in the hiring committee, we have a representative for a woman, a representative for a disabled person, and then of course other people are there, students are there. So, and there's one more person who has nothing to do with physics, chemistry, or engineering. Another person from other discipline, like in social sciences, law, or medicine. So that person is also there. He's a neutral person. He or she will not talk anything and then make a protocol and report to the rector, okay, or to the rectorate. So this is one thing. The other one is, okay, I'm at the TU Dresden, and there the rector, she was in Columbia University for 12 years. She was hired to come to Dresden. And she made it a policy that we need to strengthen women. And now her whole rectorate, 80% are only women, okay? Planning, finance, everything, research. So and she meets all of us, all the women professors every 3 months and gets a feedback, is everything going on well? How can we encourage women in research, So such things happen. And the last thing is, we as professors, male or female, we are asked to go to the schools and show ourselves as role models, okay, especially for women, to encourage students who are pupils, There are people who have gone to such heights. So these are some measures, maybe it happens here, okay. I'm not sure, just want to share my opinion. And one last point is, I was in IIC 2 days ago before I flew in yesterday. I asked some of my colleagues, why there has been no women director in IIC? Nobody had an answer. Thank you very much.
I think, Shikha, you want to add anything?
Yeah, just a little bit. Just in addition to this, and also what Professor Subra was saying, that we have these things that we go to conferences and make our presentations. We can have an outreach program where actually we are asked to go to small cities. See, big cities and metros still have women and of course boys also who are introduced to science, but these small towns, I see many in Odisha also, nearby areas, and also UP, Bihar, where we all are coming from, small towns. We see that children are not even exposed to science. So if we can make some kind of, I don't know if government policy is needed to for that or not, that scientists can actually be encouraged to maybe once a year go to 2, 3 places and give these outreach programs to small
I think
cities.
academy does it.
Yeah.
Academy does it.
Maybe academy does it, but in general,
But
scientists
maybe it's
are not able
enough.
to do it.
Maybe it's not
Can I
enough.
also add, even actually Department of Atomic Energy has a full-fledged outreach program and we are encouraged to do this. There's also the science education began Pratipadanik, but I agree, given the scale of India, all these efforts need upscaling.
Yeah, but scientists in general are not able to, not.
So it is not on the outreach.
It will improve, everybody doesn't have to go everywhere. I think COVID has taught us that, a lot can be reached online. And
Yeah, but what I'm saying is outreach has been a significant part of for the kind of plan proposal of the overall.
For example, when we have to send report to DST, for example, as autonomous institute, we have to give a list of outreach the institute has done. So even at the government level, we have an obligation to do this. But what I'm saying, it's India, I think it's very right. It's such a huge country. Maybe it's not enough.
Yeah, wherever the institute is, it is happening around that place, but just a little bit out or rural, it is not it.
Yeah, can I just make one quick comment? Just quick comment. So, this is completely my personal view. I have always felt that our government is way more progressive than the scientist community or anything. I mean, imagine the policies that are there in the 50s in our constitution, right? I mean, so I think our government and our constitution is way more progressive. The main problem with India is that all policies come like top down. So it should be otherwise. Then we should think that the diversity issue is a problem, and then it should be bottom up. Unfortunately, our democracy maybe is not matured enough. So probably for this outreach, even there's a lot of government policy, lot of encouragement to do that. It's for us to sort of, I think, for the
outreach is there, but that is limited to the city.
I think we are really running late.
Yeah.
So I will close this session with a last comment from Chandrima.
I just wanted to say that are we having enough research into why this is happening? Because, the psyche of it, that I don't think we really do research on. Because if you look at Norway, if you look at Finland, they have the best gender parity. But in STEM, subjects are miserably low. So why such kind of things happen? I don't think we're doing enough research, and we have been harping about this woman for quite a long time, and we are really, it's difficult to get somewhere because we don't have the base knowledge of what is happening. We're speaking about outreach and all that, but I think it's the psychology of it.
I think, to best of my knowledge, some social scientists in India does work on it, but again, the number is very small.
One thing that for this gender inclusion, one thing that the World Academy of Sciences have done, if you want to nominate a man, you have to nominate a woman.
They are very, very strict programs. So I think we had very, very vibrant discussions with lot of diverse points covered, and we still have 2 more days. So I think there will be many more discussion, and it's pretty late, but we still have one more talk. So, and it is from Bangladesh, where Hassan Bose wrote his famous paper. It's from Dhaka University. She could not get a visa, so could not come. I mean, visa was not denied, but it's pending. So she will be here online. Thanks to all the panelists. I have a pleasant duty.
Yes.
Yes.
So first of all, very sorry for the technical issue that has happened. And I would like to thank all the panelists and Professor Sahadas Gupta for kindly moderating this session. Now I would request Professor Sahadas Gupta to kindly hand over the mementos to all the panelists. Professor Chandrima Saha.
Senior.
Thank you. Professor Shubhra Chakravarti. Professor Vandana Nana. And finally, Professor Suchetana Chatterjee.
Thank you very much. My pleasure.
Once again, thank you for coming and for sharing your thoughts. And finally,
Can I have the mic? I think Rohini has left.
just let-
So I will write to her, so we will post her memento and maybe we'll Photoshop her. In a picture.
Okay, so we will break for tea for 15 minutes. The next talk, the final talk of today, the final talk of the day will start at 6:15 p.m. And the talk will be regarding days of SN Bose at the University of Dhaka. It will be given by Professor Shamima Chaudhary. So please be here by 6:15.
Ma'am, we just started in few minutes.
Sure. Do you have audience? No audience.
It's a tea time actually for 10.
Okay, okay. Let me join after 10 minutes, right?
Going to start in 2 minutes.
Keep it.
Hey, please.
Are you, can she hear us?
Yeah.
So, hi Shamima, this is Vandana here.
Hi, Bandana.
Yeah, I was looking forward to meeting you, so maybe next time. We really,
Till today, no news of getting visa, you know.
yeah, no. I
I applied over 6 weeks ago.
Oh, okay. Okay, so we look forward to your talk and maybe see you some other time. Yeah.
স্ক্রিনটা দেখছে আমাকে শুদ্ধা পিছনে একদম না
So welcome everyone. Welcome back again. It's been a long day. We had different sessions, talks, panel discussions running continuously. So I will now like to request Professor R.T. Garg from SINP to come and chair the final session of the day. Professor R.T. Garg.
Good evening, everyone. Welcome to the last session of the first day of conference on quantum science and women in quantum science and technology. And it's a great pleasure and honor to have Professor Shamima Chaudhary as the speaker in this session. She has served as the director of the Bose Center for Advanced Study and Research in Natural Sciences at Dhaka University. This is a center which is named after Professor Satyendranath Bose. She is also a fellow of Bangladesh Physical Society and is active in advocacy of women in STEM. And today she is going to talk about SN Bose at the University of Dhaka. Professor Shamima Chaudhary. So you have 45 minutes. And I will give you a reminder after 40 minutes.
Okay, thank you. First of all, I'd like to thank Dr. Tanushree Saha Dasgupta, Director of SN Bose National Center for Basic Sciences, Kolkata, for giving me the opportunity to give this talk. I was invited to give it in Kolkata, but because of visa issues, I'm unable to attend it in due time. But she made it possible to deliver it online. Thanks very much to Tanushree and her whole team. Ladies and gentlemen, good evening to you all. Today, I'm going to talk about famous S.N. Bose, who spent his golden 24 years in research and teaching at the University of Dhaka since its founding in 1921. My teacher was a direct student of Bose, and I met 4 more people who were close to him and heard a lot about him. I'm going to tell about them also. I'm going to present a PowerPoint presentation, including clips of video recordings. I hope you will enjoy this. The title of my talk is S.N. Bose at University of Dhaka. University of Dhaka was established in 1921. The first Vice Chancellor was Dr. P.J. Hartog, started with only 9 departments, and physics was one of them. And it started in Curzon Hall. Curzon Hall was established in 19. Sorry. Curzon Hall was established in 1904, and its whole work finished in 1908. This one is the photo of Curzon Hall in 1921. And this is the recent photo of 100 years, 2021. It's the same building, nothing has been changed. This is a black and white photo, and this is a colored photo. And this is the Department of Physics, also situated in Curzon Hall. The Department of Physics is this one. This is a very recent picture. Last month I took it. And this is the photo of 2016, the year when I retired from the department. S.N. Bose, popularly known as Satyam Bose, did his works of his life in research and teaching at Curzon Hall in the physics department of Dhaka University for 24 years. He lived in Fuller Road, Dhaka University, in those years. I'd like to mention that I also lived in Fuller Road in the same campus. He is a pride of our Dhaka University. This is the picture of S.N. Bose in 1930 in front of his bungalow. And this is the residence of Bose in Fuller Road. It's a beautiful 2-storied building with a large garden, but unfortunately, it's no more there. S.N. Bose, a distinguished young physicist and mathematician, joined University of Dhaka as reader in physics on June 1st, 1921, with 4 published research articles. He was only 26 years old at the time. After joining Dhaka University, he made a spectacular publication only 3 years after, in 1924, and made Department of Physics and the University of Dhaka known to the rest of the world. The Department of Physics, after joining, his main task was making the syllabus of the BSc honors and MSc courses, establishing different laboratories, and mainly teaching. He used to teach quantum mechanics, thermodynamics, and radiation and relativity. Apart from theoretical physics, he established different labs of electronics, chemical physics, and spectroscopy under supervision of Professor W.A. Jenkins, the then head of the Department of Physics. Later, Jenkins became the Vice Chancellor of Dhaka University. Bose developed laboratories of X-ray crystallography, magnetism, spectroscopy, chemical physics, and theoretical physics. S.N. Bose spent 24 years, and he was born in January 1894, and his death also, I'll mention it later on. He was a reader, firstly, from 1921 to 24. Then he went for study leave to Europe, 1924 to 26. He became a professor in 1927 until 1945, the year he left Dhaka University. Then he became Dean of Science Faculty in 1927 also, until 1941. And lastly, he became Provost of Dhaka Hall, now called Shohidullah Hall, from November 1940 to 1945. Bose took a study leave from the University of Dhaka and to go to Europe on study leave with some study leave amount, and returned from abroad in September 1926. He worked with Madame Curie for 1 year in her lab to learn and to know more about X-ray crystallography. Also, he worked with Louis Broglie and Langevin. He met Einstein in Berlin and many other renowned physicists in Europe. His interaction with Einstein and other physicists is very interesting. Hermann Mach of the Institute of Physics, Berlin, said how almost everything was done in German, one of those seminars that was based on his ideas about non-classical statistics of a system, particularly of low temperature characteristics. And Nernst was sitting there, Einstein was there, and everyone interested in low temperature and statistics, and Planck was also there. Then Einstein said, well, I think this is one of the most worthwhile works of the last few years. He appreciated very much. He talked about it and asked a few questions, and Bose answered the questions, and then Ernst asked a few questions. In other words, it was a very sensational event on that day, according to Mark, who recalled in 1974. Back from Europe, he came back from Europe in September 1926. At that time, the University of Dhaka advertised for the post of a professor in physics. So eventually many people applied. Bose also applied. As we all know that he did not do any higher studies like PhD or doctoral degree. So he applied for the post. For him, Einstein and other renowned physicists, they strongly recommend for him to the Vice Chancellor for his professorship. So he was appointed a professor and head of the department in February 1927. He became Dean of the Faculty of Science in the same year, member of the Executive Council, University of Dhaka. Executive Council, nowadays we call it syndicate, highest body of the university to look after everything. And he became a member of the Academic Council also, University of Dhaka. Then around 1940, he became he was appointed a provost of Dhaka Hall. Nowadays it's called Shohidullah Hall, in addition to his duties of headship and deanship. The hall is just like a red building built around the same after Curzon Hall in the same style. And there are now new building, tall building at the back, but the university has kept the old structure also, where Schotten Bosch used to work as a provost at the ground floor of this building. Bose was very much attached to Rabindranath Tagore and he dedicated his science book, Vishwa Porichoy, to Bose in 1937, his only book on science. Schotten Bosch was very much attached to his own mother language. He used to say, যারা বলেন বাংলা ভাষায় বিজ্ঞান চর্চা হয় না, তারা হয় বাংলা জানেন না, নয় বিজ্ঞান বোঝেন না. Means those who say that science is not practiced in Bengali language either do not know Bengali or do not understand science. Overall, Bose was a very versatile person. He was one of the most cultivated men. He had a mind wonderfully open, bright, versatile, and many-sided. A polymath having a wide range of interests in varied fields, including physics, mathematics, chemistry, zoology, mineralogy, biochemistry, philosophy, arts, literature, and music. He was very fond of music. In his leisure time, he used to play Israj in the University of Dhaka also when he was there. But his welfare of the university and the physics laboratory in particular were always nearest to his mind and heart, and a very dedicated person for the physics department. Bose did a lot of publications. Before joining the department, he had 4 publications. And just 3 years after joining, he made a spectacular publication. And these are the list of his publication in different fields: mathematical, theoretical physics, 10 papers, quantum physics and quantum theory, 3 papers, chemistry, chemical physics and spectroscopy, 3 papers, classical statistics, 2 papers, and Schotten Bosch actually famous for Bose-Einstein statistics and Bose-Einstein condensate. The inception of Bose-Einstein statistics was when he was teaching Planck's law in the class. And while presenting the lecture at the University of Dhaka in radiation and ultraviolet catastrophe, Bose intended to show his students that the contemporary theory was not adequate because it predicted results not in accordance with experimental results. In the process of describing this discrepancy, Bose, for the first time, took the position that the Maxwell-Boltzmann distribution would not be true for microscopic particles, where fluctuations due to Heisenberg's uncertainty principle will be significant. So he stressed the probability of finding particles in the phase space, each state having volume h cube, and discarding the distinct position and momentum of the particles. So Bose, while teaching Planck's law, he wrote an article and sent it to philosophical magazine in London. And then after 6 months, they rejected it. They rejected it and saying that it's it's not worth publishing in there. So he wrote a letter to Einstein. He wrote, "Respected Sir," you can see here, "Respected Sir," dated 4th June, 1924. I have ventured to send you the accompanying article for your perusal and opinion. I'm anxious to know what you think of it. You will see that I have tried to deduce the coefficient 8 pi nu square by c cube in Planck's law, independent of classical electrodynamics, only assuming that the ultimate elementary region in the phase space has the content h cube. I do not know sufficient German to translate the paper. If you think the paper is worth for publication, I shall be grateful if you arrange for its publication in Zeitschrift for Physik. Though a complete stranger to you, I do not feel any hesitation by making such a request. Because we are your peoples, though profiting only by your teachings through your writings. I do not know whether you will still remember that someone from Calcutta asked your permission to translate your papers on relativity in English. You acceded to the request. The book has since been published, and I was the one who translated your paper on generalized relativity. Yours faithfully, S.N. Bose. So the interpretation of Bose statistics, the reason Bose produced accurate results was that since photons are indistinguishable from each other, one cannot treat any two photons having equal energy as being two distinct identifiable photons. By analogy, if in an alternate universe coins were behave like two photons, the other and other bosons, the probability of producing two heads would indeed be 1/3. See, if coins are indistinguishable, the probability is 33% only. Bose's interpretation is now called Bose-Einstein statistics. The result derived by Bose laid the foundation of quantum statistics, and especially the revolutionary new philosophical conception of the indistinguishability of particles as acknowledged by Einstein and Dirac, both of them. When Einstein met Bose face to face, he asked him whether he had been aware that he had invented a new type of statistics. And he very candidly said, no, he wasn't that familiar with Boltzmann's statistics and didn't realize that he was doing the calculation differently. He was equally candid with anyone who asked. Then comes Bose-Einstein condensation. Einstein also did not at first realize how radical Bose's departure was. And in his first paper after Bose, he was guided like Bose by the fact that new method gave the right answer. He compared it to the wave-particle duality, saying that some particles did not behave exactly like particles. Einstein adopted the idea and extended it to atoms. This led to the prediction of the existence of the phenomena which became known as Bose-Einstein condensate, a dense collection of bosons, which are particles with integer spin, named after Bose, which was demonstrated to exist by experiment in 1995. And this year, so he published his article in 1924, and this is 2024. So this year is the 100th anniversary century of Bose-Einstein statistics. And I'm very happy that Calcutta is celebrating this. And Dhaka University will also doing a lot of programs regarding this. The transition between the old quantum theory and the new quantum mechanics, according to Partho Ghosh, his last PhD student of Bose, stated that Bose's work stood in the transition between old quantum theory of Planck, Bohr, and Einstein, and new quantum mechanics of Schrödinger, Heisenberg, Born, Dirac, and others. Now, coming back to Dhaka, he's Dr. A.K.M. Siddiq, a direct student of S.N. Bose. He was doing MSc with Bose at Dhaka University. Later on, he became a faculty of physics. He was my teacher. He was my head of the department, chairman of the department, pro-vice chancellor, and vice chancellor. And this gentleman is talking about his teacher at the age of 93 years in 2017. He died in the year 2018. I'm just amazed what a memory he had.
স্যার সত্যেন বোস কি আপনাকে পড়াতেন?
It's in Bengali.
কি
I hope you can
সত্যেন
hear
কি
him.
পড়াতো?
হ্যাঁ।
কোয়ান্টাম মেকানিক্স।
ও কেমন পড়াতেন স্যার?
হ্যাঁ, কোয়ান্টাম মেকানিক্স পড়াতো। তো উনি তো বই নোট টোট দেখতেন না।
না।
চেয়ারে থেকে আমরা বারান্দা জ্বালাতাম। সত্যেন বোসের বিয়ের ছেলেটার নাম হীরালাল।
হীরালাল দা।
হীরালাল বলল যে স্যার ছাত্ররা আসছে। আমরা অল্প জন 15 তে আমরা ঢুকলাম। আমি পরে বসলাম। বসার পরে সত্যেন বসার কোনো কথা নাই, চপ ইটি নাই, ওই একটা চপ শুধু নিয়ে বোর্ডে যেত, নোট টোট কিছুই না।
স্যার কোন রুমে ক্লাস হতো স্যার?
উনি যে কোয়ান্টাম মেকানিক্স বলতে বুঝতাম না তখন, ইট ওয়াজ ডিফিকাল্ট, একটু একটু আইডিয়া পেতাম।
স্যার কোন রুমে পড়াতেন? কোন রুমে পড়াতেন?
আমি না, ওটা সেকেন্ড ইয়ারে।
না, কোন রুমে মনে আছে স্যার?
না, কোয়ান্টাম মেকানিক্স ওইটা তো সেকেন্ড ইয়ারে উনি পড়াতেন, ফার্স্ট ইয়ারে পড়াতেন না।
সেকেন্ড ইয়ার মাস্টার্সে? সেকেন্ড ইয়ার মাস্টার্সে এমএসসি
সেকেন্ড ইয়ার,
এমএসসি সেকেন্ড ইয়ার,
এমএসসি সেকেন্ড ইয়ার। হ্যাঁ।
কোন রুমে ক্লাস হতো স্যার?
হ্যাঁ, কোন বসারে?
কোন রুমটাতে ক্লাস হতো? কোন ঘরে, কোন রুমে ক্লাস হতো? ওনার হেডের রুমে না অন্য রুমে? ক্লাসটা কোথায় হতো?
কোন রুমে?
হ্যাঁ হ্যাঁ হ্যাঁ,
ওনার ক্লাসটা ডিপার্টমেন্ট ওনার রুমেই।
ওনার রুমেই,
ওই সিক্সটা হেড যে
হেডের রুমেই হতো ক্লাস।
হ্যাঁ, সেই ঘরেই পড়াতেন, উনি অন্য ঘরে যেতেন না।
ও আচ্ছা,
ওখানে বোর্ড ছিল,
বোর্ড
ছিল, তার চেয়ার 15-20টা বেশি, তখন তো ছাত্র সংখ্যা কম ছিল।
জি, 15 জন।
15-20টা চেয়ার থাকতো, ওই ঘুরিয়ে দিল, বাস ওইখানে ক্লাস হতো। সত্যেন বোসের সঙ্গে আমার ঘনিষ্ঠ সম্পর্ক ছিল।
হীরালাল, যোগেন্দা।
হীরালাল ছিল,
যোগেন
মনে আছে না?
হ্যাঁ স্যার, হীরালাল
তো ফার্স্ট ইয়ারে।
হ্যাঁ স্যার,
দেখা তখন তো অনেক মেয়ের মধ্যে খেয়াল থাকার না, এখন বলে দিলে।
হ্যাঁ, হীরালাল, যোগেন্দা, যোগেন ছিল,
যোগেন্দ্র, হ্যাঁ
ল্যাবে ছিল যোগেন,
মনে আছে।
তারপর ভানুদা,
হ্যাঁ,
গঙ্গাদা।
ও তাহলে তুমি আমার সবাই।
So, mentioned by Professor Siddiq that Satyam Bose used to teach him quantum mechanics in the second year, final year master's class. And he did not use any notes or any paper. He used to write in the board or in the department head's room, in the blackboard. And he had chairs for the students. And what mentioned by that Hiralal, who directly worked with Bose as his bearer. And from Hiralal, I heard a lot about S.N. Bose, that S.N. Bose, he used to live in Dhaka, Bangladesh, and his family was in Calcutta. So he had plenty of time to spend in his research and in his work and teaching. So he used to come early in the morning and stayed up to sometimes late night, sometimes 9 o'clock. And he used to write and then tear it and throw the paper in the basket and used to do this. And the students would come and collect those papers when they had to submit their thesis. So they would copy those papers according to Hiralal. And then Satyendra Bose would say, Kire Hiralal, these are all looks very familiar to me. Hiralal would say, okay, Babu, you wrote all these and your writing, the student has submitted you. You don't have to this very much. And this is the nature of, he was very much close to the students. And the other person, Jogendro, was a lab attendant. He was when I was a student in 1967, he was a lab attendant in my second year class. And he was associated with S.N. Bose for setting up different laboratories also. Then Bhanu used to keep the key for the whole department, and he was the key man. And all the keys in the evening, when after closing the department, they were kept for the night at the bungalow of S.N. Bose. Then comes another person, Ganga. Ganga had a canteen in Curzon Hall where we used to eat a lot of snacks and tea, and also Satyendra Bose and all other persons they used to eat. All these people I have met, I've talked with them, and they talked a lot about Bose to me, and they all retired and passed away. And while at Dhaka University, Bose had other duties other than Dhaka University. He attended Science Congress session in Bombay as delegate of Dhaka University in January 1933, delivered lecture in Education Week in Kolkata, attended Science Congress at Benares in 1941, attended meetings of Agriculture Research Subcommittee and Indian Central Youth Committee in July 1942, appointed chairman of the Weights and Measures Committee by the Government of India, attended Executive Committee meeting of Indian Science Congress held in Kolkata, December 1943, appointed as General President of the Indian Science Congress held in 1944, delivered convocation lecture at College of Engineering and Technology at Jadavpur, March 1944, attended meeting of Bengal Industrial Research Committee as a member in December 1944. So these are, I've mentioned his duties, other duties while he was working at Dhaka University. Then in 1945, he got an offer from University of Kolkata as Khaira professor, and to join there, Bose resigned from his position of head professor and provostship from Dhaka University. And the university reluctantly accepted his resignation letter with effect from October 1, 1945. And after that, the Executive Council gave a big appreciation from the University of Dhaka to Satyen Bose. I've written this with inverted comma. The Executive Council of the University of Dhaka, in its meeting held on 10th November 1945, placed on record their high appreciation of the distinguished research rendered by Professor S.N. Bose as professor and head of the Department of Physics, Dean of the Faculty of Sciences, Provost of Dhaka Hall, and as a member of the Executive Council and the Academic Council. Now, Bose left us in 1945, Bose and Bangladesh. Professor Ajay Rai, my another teacher, while he was a student in 1957, he went to India Science Congress, and there he met Bose. According to him, whoever visited him, he inquired about the department, the students, teachers, Curzon Hall, his old home in Dhaka, and the University of Dhaka. He used to become nostalgic, remembering those 24 golden years spent in Dhaka. He previously instructed his secretary, whenever these Dhaka boys come to see me, allow them. He used to ask many childish and amusing questions. If Dhaka Bakurkhani are still available, this is the picture of the Dhaka Bakurkhani. If those palm trees and Krishna Chura are still seen, this is the Krishna Chura. If his old residence is still there, he was a friend of our liberation war in 1971. He gave not only funding, but he gave shelter to many of our physicists whoever went to meet him in 1971. Then in 1973, Bangladesh Physical Society was formed, and it was decided the Bangladesh Physical Society will invite Bose as the chief guest for their meeting or conference to be held in 1974. And I became a life member of Physical Society in 1973, and I'm also a fellow of this society. Then his former student, Professor Siddiq, and Professor Harun Rashid is the student of Professor Siddiq, and few others went to Kolkata to invite Bose for this meeting. He was so eager to come to Dhaka to visit again, nearly after 29 years. But his sudden death on 4 February 1974 couldn't make it possible. After his death, Dhaka University honored him with a posthumous D.Litt degree and established the Bose Center from July 1, 1974. The center gives projects to the faculties of the science faculty, and also gives fellowship to the students for doing research for their MPhil and PhD. I was the director of the Bose Center. I was appointed, it's an additional duty, in 2010. Then 2011, I observed the death anniversary and birth anniversary of S.N. Bose for the first time in the University of Dhaka. And since then, I was there for 7 years. Every year, I used to observe his birth anniversary, and I hold I did 2 international conferences and one international workshop with the CERN people and many seminars. Professor Partha Ghosh also went to this talk, and also Dr. Jahid Hassan, a professor in MIT who is very famous for this. And he also came along with many other notable physicists, and mathematician also came to deliver lecture in the Bose Center. And when I was the director, I proposed to the university authority in its council meeting to have a S.N. Bose Sriti museum to honor him. And ultimately, with about 4 years fight, we could establish a room where he used to sit there to honor this S.N. Bose museum, where only his easy chair where he used to take rest, his bookshelf, his revolving chair, the table, and his resignation letter, the letter written to Einstein, everything is inside that room and nothing else. And though Satyam Bose didn't get any Nobel Prize for his seminal work, but we are happy that half of the particles in this world are named after him, boson. This is my interview on BTV, it's a part of it in Bangladesh television. It's also in Bangla. It's a couple of years ago.
বোজন বলি সত্যেন বোস নোবেল বিজয়ী না হয়েও এই তার বোজনের মাধ্যমে সারা পৃথিবীতে অমর হয়ে তাত্ত্বিক পদার্থবিজ্ঞানে বেশ আলোড়ন সৃষ্টি করে তার প্রকাশিত Now, coming back to the end of my talk, I just want to, because it is a program of the Women in Quantum Science and Technology, I want to share or put some few questions to the audience for recent and future challenges. That can we design a superconductor that will work at room temperature? Can we design a drug to person specific like paracetamol? Can we have energy efficiency in materials? Can we design programmable matter? Can we transform information? How to solve traffic jam by designing DPS, not by building flyovers. The IT revolution and quantum information age. And last of all, quantum computing. We all know that all over the world, this quantum computing are being researched by a group of scientists and engineers all over the world. So these are my questions to the young scientists, especially women scientists, whether they can meet any of the recent or future challenges. So I thank you all for your patient hearing. I hope you understand this little.
Thank you, Professor Chaudhary, for a very interesting and inspiring talk on Professor S.N. Bose. We have now the session is open for some comments or questions from the
Yes.
audience.
I think Professor Bose took a lot of initiative in building up the crystallography activity in Dhaka University. So could you say a few words on that? How it was done in terms of, setting up a lab specific for that, where there was not something specifically for crystallography?
Yes, you are asking about setting up labs, right? Crystallographic lab. Yes, he was a born genius. He was a born genius. When he went to Dhaka College, where his friend Meghnad Saha studied, he went to Dhaka College and saw this bit of thing, a key and some of the scattered things. He wrote a letter to Meghnad Saha that I just feel like making some apparatus with using those. So he, after coming back from Europe, he tried to build the spectroscopy. He tried to work, because he worked for 1 year with Madame Curie in X-ray crystallography lab of Madame Curie. So he made a spectroscopy, and at that time, W. Jenkins, he also did some spectacular experiments, emission from bulb. With that experiment, he got a DSc degree from UK. So Satyendra Bose was very curious about everything. Though a mathematician, he was keen in all other subjects.
Thank you.
Any other comment or question? Well, if not, let's thank Professor Chaudhary again for being with us so late in the evening and for a very inspiring talk. Thank you.
Thank you.